Sit down. Thank you. Thank you very much, everybody. Good morning. Welcome to Dublin. For many of you, I know it's the very first time in Dublin, so I hope you find the time to go around and see the historical sites. Sven is taking photos already. Okay, so as you've noticed, we've got a lot of competitions. The descriptions are all on the website, but I will also give you another overview towards the end of this session. The reason we're hosting the conference in this historical building is because it is a very important building. And our very first speaker, the CEO and Registrar of DIAS, will tell you all about it. Eucharia, please.
Okay, thank you very much. First thing to say is I won't be telling you all about it because in the, I think, probably 8 minutes that I've been allocated to cover the history of DIAS and all that has happened would be indeed a challenge. So what I want to do really is just give you maybe a flavour of the history of the organisation. But before that, I just want to, on my own part, officially welcome you as well to the Dublin Institute for Advanced Studies on my own part and on behalf of the Institute. And we are delighted to be hosting this very special event anticipating Ireland's membership of CERN. And you'll hear a little bit more about that in a few moments from Sinead Ryan, the next speaker. DIAS is set up as a government entity under legislation. It was established in 1940 to focus on fundamental research. I now am going to take a nice shortcut very shortly because what I'm actually going to do is, after submitting a few more remarks, is show you a video that was prepared for our 80th anniversary in 2020, a 5-minute video, which attempts to, I suppose, encapsulate the history of DIAS in that 5 minutes. It's in no way comprehensive. When people see it, they often say to me, oh, you didn't mention this and you didn't mention that. But I suppose the purpose of the video is not to be an absolute accurate historical record, but is to actually give you a sense of the type of work and research and I suppose some of the key moments in the history of the organisation. One thing I do want to cover before showing you the video is just to say a little word about the actual motivation for the establishment of the Institute, which isn't actually covered in the video. The Institute was established by a former Taoiseach Prime Minister called Eamon de Valera. And I think most of you will probably be broadly aware that Ireland achieved its independence in the 1920s. Eamon de Valera was one of the revolutionaries who survived, if you like, that engagement with the British, and became the leader of the country. He himself was a mathematician and was very interested in academic affairs. And his biographers have shown that he wanted to somehow, even though the country was in dire economic straits at that time, after it got its independence, to somehow do something that would actually demonstrate to the world that Ireland still could have an impact in science. Because, of course, under its colonial past, it had a strong scientific record, and he wanted to quickly try and do something that would show that the new independent state actually still could have an impact. And in the early 1930s, he became aware of the establishment of the Institute of Advanced Studies in Princeton, and the fact that it had been established by attracting Einstein to join it, and obviously it was funded privately by the Baumbergers. So we set about setting up the Institute, and that really was the motivation for its establishment, and the Institute becoming the first independent institute for advanced studies in Europe. He obviously then wanted to attract an eminent scientist, in the same way that Princeton had to set up the institute. And the scientist that he eventually, after approaching a number of others, and there's a long scale, as they say, a long story about how all that came about. But Erwin Schrödinger became the first director of the School of Theoretical Physics, and in effect, I suppose in today's parlance, was the rock star that actually was attracted to help the establishment of the institute. And of course, very fittingly, this event today is being hosted by the School of Theoretical Physics. But subsequent to Schrödinger's time here, clearly, there was a long list of other eminent scientists who actually worked in the School of Theoretical Physics, including Walter Heitler, John Lycan-Singh, Charles Lanchas, Lachlan O'Rafferty, and Werner Nahm, to name but a few. Some of those names will be familiar to you depending on what area of theoretical physics you're actually in. So I just wanted to say a little word about the motivation as to how it actually came about before just showing you the video. The final thing I would just say is, of course, that the video, as I said, was done to mark our 80th anniversary, which was sadly in 2020. So you can imagine that our program of events got somewhat disrupted, but we're actually hoping to have almost a rerun for our 85th anniversary next year, and hopefully we'll be having some events that hopefully we might see some of you return to. I look forward to engaging with some of you on a bilateral basis over the course of the next few days, and I actually would hope that you all enjoy your time here. And before just showing you the video, there's just one quick update I would make. Probably there's a lot of things that I could say, probably even updated in the last 4 years, we could say. But one thing I will just highlight is the fact that the Institute was Ireland's only scientists involved in the development of the Webb Space Telescope. DIAS actually had scientists that co-developed the Murray telescope, one of the 4 telescopes on the Webb Space Telescope. So I suppose in the last 4 years, if I was to pick out a highlight, sitting on Christmas Day a year and a half ago, watching the launch, while my family were going, "Why are you watching this and not spending time with us?" is probably one of the highlights I pick out that's not included in the video. But as I say, there's lots not included in the video. So without further ado, I will wish you Majin Mai, which in our native Irish language is good morning. So if you're going to learn any Irish when you're here, those are 2 very important words, Majin Mai, good morning. I wish you a good morning and every success, and I hope you enjoy the conference. Without further ado, I'll ask Jeff to roll the camera there and show the video. Thank you.
Research that enables progress through creativity and innovation has accelerated at a staggering pace since the 1940s. Breakthroughs in technology, space travel, as well as evaluating our past and understanding our planet have been exciting topics during this time. For 8 decades, the Dublin Institute for Advanced Studies, or DIAS, has been at the forefront of that research and has continually explored the big questions of the 21st century and beyond. DIAS has pushed the boundaries to explore and discover the unknown. Today, the institution continues to pioneer in its main disciplines of Celtic studies, theoretical physics, astrophysics and geophysics. It has become a shining jewel in Ireland's significant scientific contribution to the world. Founded in 1940 by the Taoiseach Eamon de Valera, who through skillful negotiation and an impending war convinced Nobel Prize winner Erwin Schrödinger to be the first director of its School of Theoretical Physics. By 1943, Schrödinger had delivered the What is Life lectures, which were on their way to becoming an influential little book by the same name. That little book is acknowledged publicly by Crick, Watson and Wilkins to have significantly influenced and inspired their discovery of DNA. At the same time, the School of Celtic Studies began with Osborne J. Bergen at the helm in 1940. 6 years later, the first volume of Celtica was published. It remains the foremost journal for Celtic studies worldwide. In 1947, the School of Cosmic Physics was established. and ownership of the Dunsink Observatory was transferred from Trinity College Dublin. Spearheaded by DIAS, the first ever cross-border agreement between Northern Ireland and the Republic was signed that same year, leading to the international sharing of the large astronomical equipment for the first time. Reflecting the trend of attracting international talent to Ireland, László Joany became the first head of the Cosmic Rays section of the Astrophysics Department, and Leo Polak is appointed the first head of Geophysics. Polak goes on to propose that the Earth is getting warmer, and skerries in Dublin could be like the south of France in years to come. In 1960, J.L. Singh published Relativity, the General Theory, emphasizing its geometrical aspects, and throughout the 60s, DIAS became the leading world centre for research in general relativity. This work had a profound influence on the work of Penrose and Hawking, on black holes and the geometry of the universe. In 1972, and in partnership with University of Berkeley, DIAS professors Dennis O'Sullivan and Alex Thompson work on the first ever Irish experiment in space on the lunar surface as part of the NASA Apollo 16 mission, launching space physics research in Ireland. The Irish National Seismic Network was established in 1978, a key national resource in detecting earthquakes and other seismic activity. DIAS operates and maintains this resource. That same year, D.A. Binchy's Corpus Juris Hibernici is published. This key publication was the fruit of 30 years of work on early Irish law texts, the Brehon Laws, and laid the foundation for study in this area. It profoundly changed perceptions and understandings on all aspects of early Irish history and society. DIAS researcher Brian Jacob starts a new project in 1987 in cooperation with University of Hamburg and UCD. This leads to an expansion of Ireland's maritime territory by the mid-90s. In 1999, the Irish Script on Screen project was launched as one of the first specialist manuscript digitisation projects established in Ireland, and one of the longest running in Europe. Contributing to the conservation of valuable books and documents, it made primary materials of Ireland's cultural heritage available to scholars and students. Throughout the 90s and early 2000s, cosmic physics had the first Irish experiments performed on the International Space Station, the launch of the HESS telescope. Work on space technology continues to this day. Also in 2000, DIAS professor John T. Lewis founds Corville, which would become a major telecommunications analytics company. Geophysicists in 2016 and 2017 were busy building critical insights into understanding volcanoes and the structure of the Earth's upper crust, leading to improved forecasting of volcanic eruptions. In 2018, DIAS Dunsink Observatory was designated a European Site of Historical Significance by the European Physical Society. DIAS seeks to understand the complex underlying mathematical principles of everything, to understand through advanced physics our universe, our planet, and our island, and to understand ourselves as a people both past and present, with insights from Celtic studies. We will continue to reach for the stars, listen to our planet, explore worlds through words, and unravel the mysteries of quantum, infinity, and beyond. DIAS discovers.
Good, so you've made my job so easy. You've all heard about DIAS and why we're hosting the event here. And then the significance of the event is the fact that Ireland is finally joining CERN. And we owe that partly to Professor Sinead Ryan, who's the speaker at the next talk. And Sinead will tell us all about why it took us so long. Well, I'm not sure I know the answer to that question, but I'll say a little bit.
Yeah, thanks. So thank you very much, Venus, for the opportunity just to say a few words. And I know that's not why you're really here, so I will be quite brief so that you can get on to the real meat of the conference. I would like to take a minute, first of all, as Eucharia has done, to welcome you. For those of you who are here for the first time to Ireland, you're very welcome. It's really great to see a community of theoretical and experimental physics gathering here together in Dublin to celebrate also our journey towards CERN membership. Before I start, I also wanted to say a very sincere and heartfelt thank you to Venus for organising this conference. Those of you who have looked at the poster will see that there are a number of names on the local organising committee, but I can tell you, I'm one of those names, but I can guarantee you that all of the work, all of the hard work is done by Venus. So thank you, Venus. So Venus asked me to say a little bit. This conference is partly to celebrate our, and I have, maybe I should have also put hopefully in there, but finally Ireland's membership of CERN. For those of you who don't know me, I'm based at Trinity, which is just down the road here, where I'm working Lattice QCD, and I'm also the co-chair of the Ireland CERN Users Group. So the problem that we were trying to solve is the following, essentially illustrated by this map, which I took from the CERN webpage. It may have changed, it's quite a dynamic map, but it shows you the member states and the countries that have associate member status and various agreements with CERN. And you see, so here you are, you're all sitting here somewhere. We have no agreement, no membership status with CERN at the moment. And this is obviously is anomalous, certainly within Europe, and something that we have been attempting and campaigning to change for quite some time. So as part of the effort in recent years, a few of us realized that what we needed to do, there's a small community of particle physics in Ireland, in theory and in experiment, and we realized that what we really needed was a sort of coalition of participants who were enthusiastic about CERN membership and were not just particle physicists, but a broader community, and we gathered people together in what is the CERN Users Group. From all across Ireland and from many different disciplines. So I'll say a little bit about that in a minute. But maybe before I go into just where we are today, let me just remind you. I mean, Eucharia has already said a really nice introduction to DIAS, but there's been particle physics theory and experimental activity in Ireland for actually a very long time, despite our lack of membership of CERN. So you can, I mean, in some sense, you can trace a lot of the activity back to this gentleman here. So this is William Rowan Hamilton, who was, I don't need to tell you who he was. He's, of course, an extraordinary mathematician and mathematical physicist. He spent, for those of you who don't know, he spent his entire academic career in Ireland. He was an undergraduate at Trinity and was so astonishing as an undergraduate that before he finished his undergraduate degree, he was already appointed to a professorship at Trinity. That doesn't happen anymore. Slightly more torturous path. But it tells you something about the promise that was seen and his already very genius. He was appointed as the Andrews Professor of Astronomy, and he was the Astronomer Royal of Ireland in the 1800s. And as part of this position, as Astronomer Royal, he also had duties in Dunsink, where you will be on Friday, I believe. And so he's, of course, famous for many things. We know him for his Hamiltonian formulation of classical mechanics, but of course his flash of inspiration and genius, if you like, was the discovery of quaternion algebra, which again was along a beautiful walk from Dunsink into Trinity, where he was coming to do some lecturing, which he scribbled the quaternion algebra on the bridge, and so there's a very nice story that goes along with that. So from Hamilton, here's a picture I actually took this is a DIAS picture from DIAS of a colloquium that was hosted. So Schrödinger is here, so as you know, he was director of the School of Theoretical Physics, but here's Raymond de Valera that you heard about from Eucharia. But there are many luminaries here, but let me just point out a few. Max Born is here, Dirac is here, Heitler is here somewhere. I never remember which one he is. He's here, I think. So this was the sort of the lineup at colloquia in DIAS in those days. So extraordinary activity in theoretical physics and particle physics. Down here is Ernest Walton, who together with Cockcroft was working with Rutherford, split the atom in Cambridge and received a Nobel Prize. Walton spent his academic career in Trinity after his work at Cambridge. And because this conference in Venus has done such an extraordinary job of gender balance in our speaker lineup, I wanted to also make the point that there have been extraordinary contributions by Irish women over the years as well. This is Sheila Tinney, who did her PhD with Max Born in Edinburgh and did seminal work also with high cosmic radiation. And here's Anne Kiernan, who did her undergraduate degree and PhD in University College Dublin before moving to the US, to Berkeley and then to Stanford, and leading the US team that at CERN that discovered the W and Z bosons. So there's a long history that we're building on in our journey towards CERN membership. You will also know, of course, hopefully, that even the words we take for granted in particle physics come from Ireland. So this is a passage from Finnegan's Wake by James Joyce. And for those of you who are new to Dublin, you will, I am absolutely certain, get an opportunity to hear the call of the seagulls, which apparently inspired this line that you have from Joyce. So 3 quarks for Ostermark. Okay, so where are we today? So you've heard a little bit about the history. So this is from our CERN Ireland users group, and I really wanted to make the point there's a broad set of activity, of course in experimental and in theoretical particle physics, but more broadly than that, all linked to CERN activity. But just to give you a highlight of the things we're sort of interested in this room. So on the experimental physics side, there is a small but very active group in experimental particle physics at UCD, University College Dublin, led by Ronan McNulty, who is my co-chair of the Ireland CERN users group, and also Martin Grunewald, who is a member of the CMS collaboration. So Ronan is in LHCb and Martin at CMS, and together they have supervised PhD students and postdocs who've all taken part in those experiments. More recently, as in a few months ago, where are we now? We're in 2023, so not so long ago, Trinity also joined CMS as an associate member. So we don't have experimental particle physics activity in the university, but we have a lot of activity in computing, engineering, and material science. And so we take part in the experiment on that side, building, hopefully now with CERN membership, towards a particle physics contribution as well. You'll know from what Eucharia has said and from the history that I showed you in the previous slide, there's a long tradition of theoretical physics research in Ireland, and more recently in these fields that are essentially based at Trinity, where I am, at Dias here, of course, at Maynooth University, which is just outside of Dublin, essentially focusing on these aspects of theoretical physics. So spreading a broad range of topics that are relevant for CERN, and there's a lot of engagement, so people are visiting scientists at CERN, spend a lot of time there, and know the CERN theory group very, very well. Again, lots of activity. In particular, Ronan is leading a group in medical physics applications with accelerator technology, together with one of the hospitals here in Ireland. And one nice story we discovered after we started the campaign for CERN membership is that actually one of our colleagues in UCC, University College Cork, so in the south of Ireland, was already collaborating with colleagues at CERN. He was a civil engineer, is a civil engineer, and was interested in essentially the engineering of tunnels. And I mean, where better to go if you're interested in the engineering of tunnels than CERN? So he was working and talking to people at CERN. His own civil engineering background was to do with a tunnel in Cork that goes under the River Lee, one of the big rivers in Cork. And so that work at CERN mapped very nicely into his work in a much more practical environment in Cork. I have one slide on sort of where Ireland sits with respect to our membership. So we are applying for associate membership with a cost which is about 1.6 million euro a year. It's not that much. I mean, of course, it's a lot of money, but it doesn't feel like a lot of money in the grand scheme of things, which does lead to the question, well, why aren't we already a member? And I don't know the answer to that. But we are planning to build capacity starting from associate membership with a review built in after about 3 to 5 years. And a national CERN strategy, which is already in development, which will be led by a department in our government for further higher education, research, innovation and science. And again, I need to call out, so Lola is sitting here as a member, representative of DeFaris, and has been extraordinarily supportive. So it's wonderful to have that government support as well and recognition that we need a strategy as we go forward. One of the key points, again, I don't need to tell this audience, but for our argument and for our campaign, has been to point out that the benefit of CERN membership goes far beyond just, and I say just in quotes, particle physics and fundamental science, but it is about the training and education of students and, in fact, their teachers as well, in science and in engineering and in computing, and the available contracts for our Irish SMEs and industries, which they will be able to bid for at CERN. So there's been a sort of a understanding and evolution of our campaign from simply advocating on the basis of fundamental research to a broader advocacy for training, education, and industry benefits. So here's the road to membership. It started in the last millennium, some time ago. I mean, I didn't want to exactly say when, because I think it probably predates even my time at CERN. When I came to Trinity, my time at Trinity, sorry, when I came to Trinity, which is more than 20 years ago, people were already sort of trying to campaign for CERN membership, but hadn't really managed to put a sort of get a critical mass together. So there were lots of efforts going on. The seminal moment for us was this joint committee of business, enterprise, and innovation, which heard testimony or got information from many stakeholders, including myself and Ronan, about the benefits of membership, and they issued a unanimous recommendation that Ireland join CERN. And that, in 2019, really was, I think, the moment at which it became clear that there was not just sort of scientific support, but actually government support as well, and importantly, cross-party. So we're at the sort of cross the parliament, so it goes across the parties in government and beyond. Of course, after 2019 comes 2020, and as Eucharia pointed out, you know, there was things rather ground to a halt at that point, and so there was a little bit of a hiatus between 2019 and 2023, when again things sprang into action, and DeFerris, which is the government department I spoke about, re-engaged very actively with CERN. This was a fantastic year of activity. The application was put together, prepared, submitted, a memo went to government which formalised that application from the Irish side, and we've already had the CERN task force come to visit just a couple of weeks ago, visiting Trinity, visiting UCD, and talking to all of the Irish higher education institutions, as well as our funding agencies and various other stakeholders. So again, kudos to Dolan, who I think was really driving that and organising all of that. And so here we are, hoping that by the end of the year, we will actually be in a position to formalise our membership of CERN, and that we finally join CERN and correct the colour in the map that I showed you earlier. So thank you very much. That was a very quick tour of where we were. And maybe one thing, I might just say one thing before I finish. At this point here in 2023 and just before, one of the key pivotal moments in this campaign that really pushed this to the top of the agenda of, in particular, the minister in question, was a meeting that we had hosted down in Trinity with the stakeholders from the CERN users group, and most importantly, our students. So a number of our students campaigned relentlessly, and I mean that in a very positive way, extraordinarily positively, constructively, and with an enormous amount of enthusiasm for membership, for their, you know, for them and for their generation. And their voice was pivotal, actually. And I think that's fair to say. Our colleagues in government have recognized that, the minister has recognized that. The voice of those students was actually was extraordinary at that moment. And so maybe if we learn anything, it is that we should listen to our students, and also that, you know, those moments can really make a difference when they have something they're passionate about, speak about, and are allowed the time and space to do that. So on that note, I will finish. I just want to say thank you very much for coming here, listening to this little story about how we finally got to CERN membership. And hopefully I will see many of you at CERN, where we will be in force, I think, as an Irish contingent once we're members. So thank you very much.
Yes, okay, great. So as you know, I've tried to be egalitarian. Everybody has 20 minutes, including their questions. But you know, if you eat into that, that takes out of your company time. So you know, yeah. I'm chairing the first session, and if you've seen me chairing, you know how harsh I am. I'll come at you with a ballboard if you don't understand. But yeah, we are already at overtime, so that's I'm sacrificing my own presentation at the end of this session. But please, without further ado.
Okay, thank you very much. Thank you for the invitation to be here. It's my first time in Ireland, and it's really, really nice to be here and nice to see all of you here. So I'm going to talk to you today about searches for additional, I see how it works. Searches for additional low-mass Higgs bosons at the LHC with results from CMS and ATLAS. So this is the Collider-Higgs part of cosmology, astrophysics theory, and Collider-Higgs. So the motivations, so we already found one Higgs boson about in 2012. So why do we still look for other Higgs bosons, and why, moreover, should they be light? So, well, first of all, there's still room, if we look at our standard model of Higgs properties measurements, there's still about on the order of 10 to 15% of space left for exotic decays of the 125 Jeff Higgs, which we know to non-standard model particles. And many BSM theories allow new light scalars or pseudoscalars. So this talk will focus on a selection of the most recent additional low-mass Higgs boson searches from ATLAS and CMS. So we'll be looking at light pseudoscalars A, either in association with, for example, a Z, or in pairs in different configurations. A standard model like or not scalar Higgs or X going to gamma gamma. This is in order of increasing mass. Then a dark Higgs boson as scalar and pseudoscalar HA, and then conclusions. And these analyses are interpreted in these theories, which we'll be hearing somewhat about in other talks during the week. Axion-like particles or ALPS, dark SUSY, vector portal, next to minimal supersymmetric standard model, 2 Higgs doublet models plus singlet, and type X 2 Higgs doublet models. Now this talk will not cover CMS Higgs and dark matter searches, so this will be Alicia Calderon's talk on Thursday, and additional low mass Higgs bosons co-produced with H125. So for this you'll need to see Jana Scharf-Smith's talk on Thursday. Okay, so for detectors and methods, briefly, these are the same analyses. Obviously, we have the ATLAS detector and the CMS detector. I don't have time to go into the details. They're general purpose experiments with a very, very wide range of capability to do standard model measurements and search for new physics. And but focusing on certain more recent techniques which are evoked in these analyses, there's been a push to look not only for resolved, but also merged diphoton and bi-B-jet reconstruction to access lower masses, a search for both prompt and long-lived decays, and then a lot of use of machine learning, ML, in a particular boosted decision trees, exploiting kinematical variables. Okay, so the first analysis is an ATLAS analysis. So we're looking for a light pseudoscalar A from the decay of the H125 Higgs to ZA going to, with the Z going to 2 leptons, A to gamma gamma, and here is the mass range, so it can be down to 100 MeV for the A mass. So this analysis exploits merged and resolved diphoton categories. If the mass is less than 2 JeV, it's considered to be a merged diphoton. If it's greater, it's a resolved diphoton. And then for the merged case, the discriminating variable is the mass, which you see here. With the data is always the points. The fit model is the blue line. The signal is the red, and you just see a little bump. It's the fit model including a signal. The backgrounds are from Z plus gamma and Z plus jet processes. For the resolved case, the discriminating variable, which I don't show here, is the delta R between the Z and the gamma. You see the Feynman diagram here. And then we Atlas places 95% confidence level limits on the branching fraction h to 125 to ZA, A followed by 2 gammas, as you see here on the y-axis as a function of NA. And you see on the left for the merged category and for the right the resolved category, and these range between 0.08 and 2%. The corresponding CMS result gives results on the order of 10 to the minus 4, but the mass range probed is not quite as large. These results are interpreted in axion-like, as an axion-like particle interpretation in the phase space of the A mass and the effective coupling C gamma gamma over lambda for several CZH values. Okay, so the C gamma gamma values is a function of MA for prompt decays only, and the exclusion given by this analysis is this blue zone for the different values of CZH, and you see other exclusions from other sources, for example, cosmological sources like supernova 1987A, other cosmological results, beam dump experiments, the LEP collider experiments, LHC, LHC experiments, indirect gamma to invisible and E plus C minus to invisible to gamma, and then the orange region is the region favored to explain the muon G minus 2 anomaly. And you see that the exclusion of this analysis cuts off some of that favored parameter space. The next analysis is almost the same. It's H125, but this time going to a pair of pseudoscalars, each one going to 2 photons, as you see here. Again, it probes very low masses going up to 62 JeV. This is also a search motivated by axion-like particle models. So here, a neural network is used to distinguish single from merged photons. So you see here that the neural network output for, it's pushing to lower scores single photons, and the merged diphotons are pushed to the higher values. So this analysis in the prompt case, which you see here for C A gamma gamma equals 1, 95% confidence level limits on the branching fraction H125 to AA with A to 2 photons are placed, they range between 2 times 10 to the minus 5 to 3 times 10 to the minus 2. That's the prompt case. For the long lived case, they range between 2 and 6 times 10 to the minus 5, for A masses between 10 and 62 JeV, and between 10 to the minus 4 to 3 times 10 to the minus 2, for A masses between 100 MeV and 10 JeV. And these are the most stringent limits to date for the long-lived case. And the interpretation in the alpha MA CA gamma gamma phase space for 2 different values of C effective AH, you see once again that this gives a lot of exclusion. It's the blue zone, and once again the orange region is the G minus 2 favored explanation region, and a lot of this is excluded by this analysis. Okay, now we move to a light spin zero boson pair produced from, this is the first CMS result that I'm showing, the other 2 are Atlas. This can be a heavy resonance X going to 2 light spin zero bosons phi. Each phi decays to 2 photons, probing this mass range. So here, the X mass, the heavy particle mass, is allowed to range between 300 JeV and 3 TeV. And a further constraint is placed on the ratio between the phi and X masses there, so they have to be between 0.5 and 2.5%. And this guarantees that only merged diphotons are produced. So here, 2 convolutional neural networks are used for the first one to address the merged mass, and the second one to classify the objects, the clusters, to be either a merged diphoton with a probability to be either a merged diphoton, a single photon, or a neutron. And you can see here a validation of this technique with boosted eta to gamma gamma decays, and you can see here in the main part of the plot that the objects that have the probability to be a merged diphoton greater than 90%, so this is quite high, and you can see clearly the eta peak. Here, there's 95% confidence level limits placed on the production cross-section, assuming 100% branching fraction to 5 phi and then later to 2 photons. And these range in the plane, in the phase space of the ratio between the phi and x masses as a function of the x mass. And these range between 0.03 and 1.06 femtobarns. This is the most sensitive search of its kind at the LHC, and the largest excess has been seen for x mass and phi mass values respectively of 720 and 5.04 JeV, with a 3.57 sigma local and only 1.07 sigma global significance. So not something to get super excited about yet. Thank you. Okay, then we move to the light boson pairs from going to form muons. So this could be model independent. Also, it could go via an H. So it's pair produced two A's. It's a model, first of all, the model independent search. Then there's a whole bunch of interpretations. So the key to this analysis from CMS is to select two isolated dimuon pairs in regimes which avoid the J-psi resonance. So here you have on each axis is one of these dimuon pairs. Here it's below the J-psi mass. This is above the J-psi mass, but below the upsilon mass. This is above the upsilon mass, so we avoid these known resonances. And then we enforce the max proximity of these two dimuon masses with this constraint. So you can see that's represented by the dotted lines here. In 2018, we were able to probe long-lived decays by using a trigger without a vertex constraint. And here you see the results. From 2017 to 2018, you have 95% confidence level limits as a function of MA on the production cross-section times the product of the two branching fractions for the dimuons, times the acceptance for PP to mu. And these range between 0.049 and 0.247 femtobarns. Also, when you combine with the prior analysis from 2016, which probed only the lower part of this mass range. Okay, that was model independent. So here we have the many interpretations of this analysis. So first, in an NMSSM interpretation, so the NMSSM interpretation, you have a Higgs boson that goes to two pseudoscalars, each giving the A1, as you know, there's two in the NMSSM. Each one goes to a pair of oppositely charged muons, and here you have the interpretation in these three plots give the interpretation in that model. The 95% confidence level limits on the product of the cross-section times the two branching fractions. And the plot on the left is particularly interesting because the assumption here is that the A1 is, that the H is 90 JeV. So you have a light, both Higgs and also A1 as function of E1. And these are for two higher masses, H1 125, which is obviously the same as the standard Higgs boson mass we've discovered, and then a higher mass, 150 JeV. Then there's the interpretation in the vector portal model, so Z dark to two dark scalars to form U. And once again, limiting here you have the kinematic mixing parameter, the square of it, epsilon times the branching fraction on the x-axis, and the limit is a function of the scalar dark mass. And once again, these red colors in the middle, red and purple, they correspond to scenarios where also the ZD has a very relatively low mass, 88 JeV and 110 JeV. And then finally, the dark SUSY interpretation, where you have a Higgs boson going to a non-dark neutralino. Each non-dark neutralino decays to a dark neutralino and a dark photon, and the dark photon decays to two muons. So this phase space is pretty well known. It's the kinematic mixing parameter epsilon is a function of the dark photon mass. And you can see that this analysis gives an exclusion for different values of the branching fraction Higgs to 2 and 1 to 2, 2 gamma dark plus 2 and that ranging between 0.5 and 0.05 and 10%. And this is a related atlas search, which you can go look up. Okay, then we move to co-production VH125, where the H125 decays once again to a pair of AA to each A goes to 2 Bs. It's a 4B final state, exploiting 1 or 2 additional leptons from W or Z to beat down the standard model background. Here you see the boosted efficiency output, which is used. There's 1 for the W case and 1 for the Z case. And you can see that the major backgrounds come from TT bar. This boosted decision tree is used as a discriminating variable, and you get 95% confidence level limits, upper limits on the cross-section times the branching fraction normalized to what it is in the standard model. They range between 1.1 to 0.36. And then this analysis gives new exclusions. It's the light purple zone that I've highlighted here in the types 3 and 4 2x doublet model plus singlet phase space. Thanks. Okay, so now we move to a standard model like or not, a scalar, Higgs or X to gamma gamma. So here I've combined the discussion of the CMS and ATLAS results. It probes ranges between 66 for ATLAS and 70 for CMS to 110 JeV. So the biggest challenge, as you can see in this little cartoon, is that these are events as a function of m gamma gamma. If you want to probe this mass range, your biggest problem is misidentified Z to EE pairs, which can fake photons. This is the fake bump that you have here. So what CMS has done is to veto tracks that are either late or are missed by our pixel detector. But we want to spare boost, as is shown in this plot. So this plot shows all these tracks, or the sum of the square of the PT of the tracks, which have really been missed, which have been missed so far. Okay, but what we want to do, we don't want to just cut these out because some of this in the signal corresponds to boosted events, which are very sensitive. So we made a cut in the two-dimensional phase space of this track variable as a function of the PT of the diphoton system. This is for signal and this is for the Drell-Yan background. So you can see that if we cut everything above this line, most of the Drell-Yan background disappears. ATLAS takes a different approach, a VDT approach, a kinematical object VDT with conversion variables. So you see the output for non-resonant diphotons. The goal is to differentiate photons from electrons, so the photons are pushed to their high values and the electrons are pushed to very low values. And then this for what is called the model-independent case, which means that the decay processes happen in the same proportions as in the standard model. This output is fed into another boosted decision tree that evaluates the diphoton itself, which favors diphoton events, and this favors non-resonant QCD gamma gamma or gamma events as well as electrons. Now the results of this analysis, which of course a lot of you are familiar with, for CMS, we see a modest excess 2.9 sigma local, 1.3 sigma global, with a mass of 95.4 JeV. ATLAS takes 2 different interpretations. First of all, what is called model independent, which means that really there is just gluon-gluon fusion, which is used as a signal model, but no, not assuming production processes in the same proportions as in the standard model. Here there's a mild excess at 2.2 sigma, local significance at 71.8 JeV. But then when they do the model dependent, as we do in CMS, the largest excess is not large, it's 1.7 sigma, but it happens to be, for the moment, at the same mass as what we see in CMS. The 95% confidence level upper limit on sigma fiducial times B is between 8 and 53 femtobarns. And then what can be compared is in the 2 model dependent approaches, the 95% confidence level upper limits for CMS are between 50 and 73 femtobarns, and for ATLAS between 19 and 102 femtobarns. Okay, almost done. I just have 2 more analyses. I'll go very quickly with them. So this is analysis from Atlas probes as the dark Higgs model. It's a dark Higgs S from a Z prime, virtual Z prime going to Z prime plus S in either of these two Feynman diagrams. So the chi here is a dark matter particle. So you get BB bar plus missing energy essentially. The backgrounds, as you can see here, are mostly from TT bar and B plus jets, B being a vector boson. Atlas can access lower scalar masses with a missing energy trigger, and then they use a dedicated merged B jet or large R or fat jet tagger. And what's done is exclusions in the NS-MZ prime plane. So in two scenarios, the first one is where the Z prime dark matter coupling is fixed, as you see here, and the exclusion is the green part from this analysis. So what's interesting is it excludes really the lowest range of the S masses. And then in the second scenario, this coupling floats to match the relic density, and the largest deviations that are seen, which are deviations, are what's the largest differences between the expected limit, which is the dotted line, and the closed line, which is the observed limit. It's seen for S masses of 60 and 60 and then 130 JeV. And the last analysis is from CMS. It searches for a new phi, either little h or big H, because the interpretation is in the type X 2 HDM model, from Z prime to phi A with a 4 tau final state, which probes for the phi between 100 and 300 JeV and for the A between 60 and 160 JeV in this diagram. So this analysis uses categories with up to 4 hadronic taus, one category with 3 hadronic taus, and then some subdivision in opposite sign and same sign, as you can see here. And the discriminating variable is the total transverse mass, which is defined here. You get 95% confidence level upper limits on the product of sigma times the two branching fractions, which are on the color axis. So these range from 1.4 femtobarns at MA of 160, M5 of 300 JeV to 20 femtobarns at 60 and 100 JeV. And then for the interpretation, this analysis is very interesting because the interpretation in the type X or lepton specific 2x doublet model, what you can see here in the phase space of tangent beta as a function of MA, the excluded region is is this light blue, and it totally covers the muon. It totally. It partially covers, the G-2 preferred region. Okay, so sorry, I probably went a little bit over. So for the conclusions and perspectives, unfortunately, no evidence for the existence of extra Higgs bosons has been found so far by either CMS or Atlas. However, only one result presented here was not performed with the full LHC run 2 data set. So we're really coming along on coming out with the results from full run 2. The perspectives for run 3, so you see where we are. We are basically here in 2024, so we still have 2024 and 2025 left in run 3. So we hope for about 250 inverse femtobarns, so double the discovery possibilities that we have now. And then the HL-LHC, the high luminosity LHC, will start in 2029 here. And we expect 3 inverse attobarns, so really an order of magnitude more than what we have now. So there's really a lot of space for discovery. And thank you very much for your attention.
The floor is yours.
Thank you. Yeah, so I want to talk to you about how we are testing the Electroweak sector of the standard model using multi-bosons, polarization measurements of multi-bosons. Okay, so first of all, let me start by telling you why I think polarization measurements are interesting. So we know that the polarization of the vector bosons is strongly related to the structure, the gauge structure of the Electroweak sector. The Higgs mechanism predicts the existence of a Higgs boson that we have found, but it also predicts the existence of some Goldstone bosons that are absorbed by the physical W and Z boson, and in this way, the W and Z boson become massive and they gain the longitudinal polarization. So we can say that longitudinal polarization is also a consequence of the Higgs mechanism. Of course, measuring one longitudinal boson, we have done that. At LEP, we saw longitudinal vector bosons. What is more interesting will be to see them interacting with each other, how they talk to each other. And one plot that we usually show in conference that I like a lot is this plot that shows here the unitarity, the cross-section versus the energy of the center of mass for the W's and the Z boson. So if you have W's and Z boson longitudinally polarized in blue and with the other polarizations combinations in gray. So what you see here is that if you remove the Higgs and you calculate the cross-section, so this is the dashed line here in blue, the longitudinal bosons see it and go crazy, right? And violates unitarity, the cross-section grows and grows and grows. While for the other combinations of polarizations, they don't see, basically do not notice that the theory doesn't have a Higgs. So what is more interesting if we are looking at vector bosons is to look at these longitudinal bosons and how they interact with each other. There is another thing that is called the Goldstone boson equivalent theorem that tells us that if these longitudinal bosons you measure at high energy, when the mass of the boson becomes negligible, then they start behaving like the Goldstone bosons. So if you measure longitudinal bosons at high PT, you are coming back to this these Goldstone bosons that come from the Higgs mechanism. So this is an important test of the Electroweak Theory. Also, it might be that new physics is hidden somewhere, right? That is something how the Higgs boson was violated. If you remove the Higgs boson, things violate unitarity. Well, it might be that new physics is hidden in this sector. It couples preferentially to some of the polarizations, and that is why we haven't seen it now yet. So, just a bit of refreshing. So, what I mean by polarization? Polarization is just simply the alignment of the spin in the direction of motion of the particle. So, what I call transversal polarization is either the spin and the direction of motion is aligned or anti-aligned, and what I call longitudinal is the spin being orthogonal to the direction of motion. So there is a caveat in all polarization measurements, and it's that, as you know, this is frame dependent. So if I change the frame of reference, then I could see my bosons being polarized in a different way. So I always have to define a reference frame every time I want to do a polarization measure. But I didn't answer the question on how we measure the polarization. So the nice thing is that we have parity violation in weak interactions. So why this is nice is because when the bosons decay, then they have some preferential directions. So angular variables of the boson and the decay products is what we use to measure the polarization in a frame that we have clearly defined. And technically, how we do this is that we perform fits. We have our data, and then we have some templates, theory templates, that we fit to our data to know if we have longitudinals or transversally polarized. Okay, so we know how to measure how we get those templates that we use for our measurements. Well, we have Monte Carlo generators. There are several in the market. Actually, this field has become active for polarization lately. The one that we have used the most in the collaboration is Matter so far. So we can produce basically leading order events calculations for this. Then fixed order calculations are available at higher orders. There we have next to leading order QCD, next to leading order Electroweak. And this is not a theory talk, but I took a theory plot to explain you a little bit the challenge. Because we have leading order generators that we can run through detector stuff. We have fixed order calculations with higher accuracy, and they show us a complicated picture. So this has here the 4 polarization states. The interesting one is the double longitudinal for Z, and you see the double longitudinal contribution is very small. So we are after a very small contribution in the whole section. The other thing is we focus on the ratio that shows us the electroweak corrections, is that different polarizations get different corrections. So the shape is different, and also the global value of the polarization is different. So if we only have leading order templates and we want to correct them to them, we have to correct each of them, not by the same value and with different shapes. So it's a complicated job, and this is one of the biggest experimental challenges that we have when we do polarization. So how to incorporate to our Monte Carlo simulations these corrections, and for that we use multiple reweighting techniques. All right, so on the experimental side, I mean, polarization measurements have been done before, right? They were done at lab with single boson polarizations. We saw first time longitudinal bosons, but we never reached observation for two bosons at the same time interacting and playing with each other. At the LHC, we are doing the same single and diboson polarizations in different diboson channels. So since I'm part of the ATLAS collaboration, I will be showing you the ATLAS result. So this one's here, and focus more in the latest one that just came out 2 months ago. So let's start with the polarization in WC. So these are the leading order Feynman diagrams that we can have at the LHC to produce WC bosons. And first thing you do, or first thing you try to do, is to have single polarizers. So this was the very first attempt that we did to do a polarization measurement, first with 36 femtobarn, CMS is the same. Actually, I said I'm ATLAS, but I'm showing you this CMS plot because we didn't have a nice one from ATLAS to explain this. But the technique to get the template was this. We generate coherent next to leading order events, these are the blue here, in the full phase space. So we have here an angular variable for since we didn't have a Monte Carlo that could generate polarization, what we do was to take the theory equations and do the fit on this full phase space, and this gives us here the transversal and the longitudinal polarization. So it fits very well, theory fits the generated events in the phase space. Now we need to do the measurement of the fiducial phase space. So what we did was to extract weights and then define a fiducial phase space. These are the templates from ATLAS. So it doesn't show the fit, but it shows the templates that we got from a fit in the fiducial phase. But the fiducial phase space is not where we do the measurement. We do the measurement at detector level. So we had to transfer this to include all the detector stuff and fit the data. And here you have it. So here is the data, same angular variable, and our template. So they fit quite well. And we were able to measure longitudinal polarization for one boson at the same time. And one boson individually, sorry. The thing is that this fit of the theory to the generated events do not take into account the correlations between the two bosons. So you can either get polarization for one boson or the other boson, but not the correlation between the two. So that was a limiting factor of diboson polarization measurement. But the next step was to do the diboson polarization. So how we did? We generate templates from MATLAB. These were merged samples, so in order plus real correction, which is great, but still very insufficient to describe our data, because it's data we have all orders, and the difference between these templates and data were about 50%, so huge differences. So to correct for that, what we did was to develop a multi-dimensional reweighting, and our theorist friends were very, very helpful, providing us multiple distributions in different phase spaces so that we could reweight all our templates to fit the data. Then we got templates. We need to look for this tiny signal that I told you, this longitudinal 7%. So, but for that, we built several categories. We split our data in regions enriched with LL, LT, and all the other combinations, and then we fit these categories. So here you have it, the 4 categories. And again, it was not enough to discriminate double longitudinal versus the rest. So what we did was to train a deep neural network to separate the different polarizations, giving the training on these reweighted events. And with this, we managed to get a first observation of 2 bosons being polarized at the same time, with 7 sigma for the double longitudinal and more than 5 sigma for all the other combinations. So this was a big success. We were also managed to do this very nice 2D contour with the 2 different polarizations being floating at the same time. So, but then the question is this really interesting, right? Is the same of measuring the probability of having one boson polarized, the other boson polarized, is the same as the probability of the 2 boson polarized. I don't know if I'm saying it right, but are they correlated? Or I can just measure the polarization of one, the polarization of the other. So to test this, what we did was to calculate this RC variable, which is just the ratio between the double polarized and the polarization of each of the bosons. And if they were uncorrelated, we will get a 1. If they were correlated as the standard model predicts, we will get a 1.3. We got 1.5 with a very large error, so we can still not exclude that they are actually uncorrelated. So, okay, but we can measure polarization, so this is great. And we got creative. So we got creative, and I said in the sense that we can go to more special phase spaces, right? And play a little bit with our polarization and the capability now to measure double boson polarization. So what we did first was to change a little bit the phase space and use our WC events to test some other predictions of the standard model. One of them is called the radiation amplitude zero effect. So this is a leading order effect that only affects transversal polarized bosons. It happens for WZ and W gamma, and what you get is that there are some strong gauge cancellation that create a drop, like a hole in the angular variable. So I'm talking now of this angle between the direction of the quarks and the emission of the boson. And you see, well, this is a simulation for different entities in the center of mass, but for all of them, you get this drop on the cross section. So can we test this in our data? This is a leading order effect. So people were saying, okay, to measure your data, you have all the orders, so it's difficult to get this. But what we did was to add a cut on the PTW set to reduce the jet activity. This is kind of a veto, right? On the jet activity to be more leading order-like. So the tighter you cut on PTW set, the more leading order-like your phase space looks like. And in this plot, you have the evolution of the data compared with the simulation, and the TT contribution is the reddish brown color here. And you see the hole in the middle of the distribution goes deeper and deeper when you cut tighter and tighter in WZ. So we do see the dip appearing. So now we wanted to quantify how deep is this hole that is appearing there. So for that, we defined a depth variable, which is it's just a very simple variable. It doesn't really have like a deep meaning on it. It's just to quantify how big is the hole. And it's just the ratio between what you measure in the size of the hole with respect to the height of the hole. So just measure counting events in this area. So to have a feeling, if you have a D equals 0, it means that this TT contribution is totally flat. If you have a D is smaller than 0, it means that actually here you have an excess, so a lot of events here. And if D is bigger than 0, it means that you actually have this hole appearing here. So we did this measurement. We did it unfolded so that we don't have detector effect and so on it for the different cuts PTW set. And what you can see here is that the measured D that we have is significantly above 0. So we exclude the no dip hypothesis. So it means that we do see this RAS effect in our data. All right, and then of course we also calculated unfolded distributions for this variable for different polarizations. The sum of the polarizations we use a lot of results with that. Then I told you the interesting thing is the longitudinal, or what we think is very interesting, how they interact to each other. So what we did was to keep the cut on the TW set. That will help us to reduce the TT contribution because of the RAS effect, and then add an extra cut on the PT of the Z boson. So this is to place yourself in this area where the Goldstone boson equivalence theorem starts to hold, right? So this interesting area where the Z longitudinal Z bosons and W bosons start to behave like Goldstone. Okay, here we did what we can with the data we have. We need to have data points, so we started at 100 GeV. We have two bits, 100 to 200 and 200 to infinity. But with this, we managed to increase the double longitudinal contribution up to 23%. So it's not anymore the 7% that you will barely see in the plot. Now we have 23%, so we have a sizable contribution of longitudinal bosons. again, it's a challenge to separate the longitudinal from the other bosons. So what we did was to train a boosted decision tree to separate longitudinals versus the rest. And you see the double longitudinal contribution is here closer to 1, this blue contribution that you can really see. And this is for the other being the angular variable. So you can really see this contribution appearing in the plots. So we did the measurement for fractions, and we also wanted the measurement to be the less model dependent that we can. So we played a little bit with our feet, either allowing the 3 fractions to be floating at the same time, 2 fractions at the same time. So okay, you have to play a little bit with your data and the limitations that you have on the number of free parameters that you can put in. But the nicest result is the one with more constrained fit, so only 2 free parameters. As you see, you get observations for the double longitudinal bosons with 7 sigma for the first bin, 100 to 200 GeV, and evidence for the more than 200 GeV PT sets, so where this Goldstone equivalence theorem starts to hold. So this is really great news. Then, of course, in Atlas we have many other bosons combinations. So I will not give you all the details for the others, but we also did for ZZ, and actually for ZZ the problem was even more complicated. So for ZZ the statistic is smaller, so we directly went for double longitudinal versus the rest, and there you also trained a boosted decision tree to separate double longitudinal versus the rest. So this is what you see here. And for the templates that I told you is the big challenge. Well, when this paper was published, we only had math graph simulations for these 2 processes, so QC ZZ and Electroweak induced ZZ plus jets. So we had somehow to manage ourselves to get prediction or a template for the gluon induced ZZ. This is no longer the case, so now it's possible to do it. But for that, we had to define a multiple step reweighting in order to get some sort of template for this gluon-induced production. The results for this channel, you can see here. So this is the final BDT score that we fit with the double step longitudinal. Here the fraction is much smaller. You remember the 23% of WC. Well, here is a smaller fraction, close to 6%. But we are able to measure it, and we have evidence for it and provided a cross-section. So I didn't say much about uncertainties on all these measurements, but it comes without saying that it's modeling uncertainties, right? It's the templates that give us the largest uncertainty in all the measurement, and of course, the statistics. Okay. The most interesting thing that I said at the beginning in the motivation was to see the longitudinal bosons playing with each other, and ideally exchanging a Higgs boson that will be like all the particles that are predicted by this Higgs mechanism playing together, so boson, boson, and Higgs. So that will be the holy grail, what we want to do in polarization measurements. So that will be a vector boson scattering measurement. Unfortunately, these days we still don't have the statistics for actually measure polarization vector boson scattering. This is one of the rarest processes of the standard model. But probably in the future, I mean, we have done a lot of progress with these measurements that we have done in the inclusive space now. These are very old projection studies that were done for the yellow report, so they are from 2018, that show what will be the expected significance as a function of the luminosity. So for high luminosity, it will be 3,000 femtobarn. So without the statistical uncertainty, with all the statistical uncertainties, we might get 3 sigma for the double longitudinal W boson. But I think these are very pessimistic. Oh, sorry. These are very pessimistic. These are a simple code-based analysis, so we can do much better. So in summary, well, our measurements, we can now measure weak boson polarization for diboson. This is really interesting. It helps us probing the electroweak, the ingredients of the electroweak symmetry breaking, and well, we have done a lot of progress, and there is a lot to come, and a beautiful collaboration between theory and experimental community to get these measurements. So yeah,
Thank you very much. Thank you, Joany. That was a very nice talk. I love how much you used your hands as well.
I'm Latin, so you know.
So we are out of time. I may allow one question, not by Sven.
So when you were talking about the joint polarization WZ measurements, you mentioned the use of deep neural networks in your analysis. Can you just say a little bit more about how those were used, what they were used for?
So the idea of this deep neural network that we used there was to separate double longitudinal versus the rest, because the fraction is really small. So what we did is that we feed to the deep neural network angular variables, and then we train it to discriminate signal versus background.
Thank you.
Thank you very much. Let's thank Joany again.
Good morning. Yeah, so I'd like to thank Venus and the organizing committee for inviting me to this awesome conference. I'm really honored to be here. So actually, today I want to talk about our recent work on very light fermiophobic exposure at the high-luminance HL-LHC. So actually, we are here to catch something very valuable, and the lineup includes various candidates. But simply saying, they are all revolving around the physics beyond the standard models. But if we focus on the LHC, actually we can say that the situation is not that satisfying. Right? So every day, it seems like every experimental paper echoes the same sentence. The observed data are consistent with the standard model prediction. So let me lift your spirit by the poem by this great Irish poet. He knows. It says, histories say, don't hope on this side of the grave, but then once in a lifetime, the longed-for tidal wave of justice can rise up. And one good example for this tidal wave is this one, very light. So these are my contents. So let me briefly review this fermiophobic explosion in 2HDM. So here we have an additional Higgs doubling field with a non-zero vacuum expectation value, and we need to avoid this true level FCNC, so we introduce discrete Z2 symmetry. Then scalar potential with the CP invariance is written like this. Then this model has additional Higgs boson. So this is lighter CP, even Higgs boson, heavier CP, even Higgs boson, pseudo-scalar, and charged Higgs boson. And according to the G2 parity of the right-handed fermions, right, we have 4 different types: 1, 2, and X and Y. But our focus is this very light fermiophobic explosion. So our setup is like this: just type 1 and the inverted Higgs scenario, which means that the heavier CP, even Higgs boson, is the observed one. And we will set this alpha, mixing angle alpha, to be pi over 2. Then, here, this is lighter CP, even Higgs boson, becomes fermiophobic. So this is called fermiophobic Higgs boson. Actually, then you may say that this model is too restrictive. Maybe you don't have much, allowed parameter space. But the answer is yes. So if you consider all kinds of constraints, theoretical and experimental, for example, for the theoretical requirements, we can demand, right, bounded from below scalar potential or perturbative unitarity, vacuum stability. For the experimental constraints, we can impose big physics result, Higgs precision data, or direct search bound. So to implement these constraints, we use the open public code Higgs signals and Higgs bounds. And in addition, our group imposed an additional condition. The cutoff scale must be higher than 10 TeV. This is, usually overlooked in other studies. Why did we impose this condition? Because in 2HDM, scalar quartic couplings run very fast under RGE. So even though you have a very stable station at electroweak scale, so your stability is guaranteed, but they are quartic couplings running very fast. So at higher energy scale, a certain energy scale called lambda, the theory may be blown up. So we can call that scale as the cutoff of this one, right? So you have to impose this cutoff scale requirement, then actually it's very restrictive. So also we did this random scan for this light fermiophobic Higgs boson in the mass range between 1 to 30 GeV, and this is a charged Higgs boson mass from 80 to 900 GeV, something like that. And these are the viable or allowed parameter space. The left one is the charged Higgs boson mass versus this fermiophobic Higgs boson mass, and the color code is your cutoff scale. So actually, this is very interesting because for these very light, this is light fermiophobic Higgs boson, there is an upper bound for your charged Higgs boson, and that bound is not that high; it's just 330 GeV scale. And this is the allowed parameter space for tangent beta versus this fermiophobic Higgs boson mass, and this is M1 square. This is the softly broken T2 parity terms. Then you have this allowed parameter points. But we found that here, this between 1 to 10 GeV, the survival percentage is significantly higher. Actually, of course, this doesn't tell you anything, right? So, okay, so this survival percentage is high, so what? But important thing is that in the literature for this fermiophobic Higgs boson is this mass range from 1 GeV to 10 GeV. Nobody has studied this LHC phenomenology yet, so it is worth investigating, right? So that's what we have done. So we considered this very light fermiophobic Higgs boson in the mass range between 1 to 10 GeV. Then this one decays into 2 photons with almost 100% branching fraction. Then what about the other BSM Higgs bosons? Actually, they also have just one dominant decay mode. This is for the charged Higgs boson. It decays into W, and this fermiophobic Higgs boson with almost 100 branching fraction. And this is the pseudoscalar. That dominant decay mode is Z boson and the fermiophobic Higgs boson. This is 0.96, so you can tell it will decay into this Z boson and fermiophobic Higgs boson. So how about this channel? This is the golden channel, we think. So it is W mediated. You produce charged Higgs boson and fermiophobic Higgs boson, and this charged Higgs boson will decay into W and fermiophobic. Then, and let's consider the leptonic decay mode of the W boson. Then what is the final state? 1, 2, 3, 4. We have 4 photons, 1 lepton, and large missing transverse energy, right? So what about the cross-section? As I told you, there is an upper bound for this charged Higgs boson. So this is the parton level cross-section, and it is not that small. The cross-section is of the order of 10 to about 100 femtobarn. So, okay, it's very promising. You can say that, actually not. Why? Because of this very light mass of the fermiophobic Higgs boson. So it's a little bit different from Susan's case. It is boosted, much boosted. Susan considered this 125 decaying to light Higgs bosons. In this case, fermiophobic Higgs boson and charged Higgs boson, they are more boosted. So 2 photons are highly collimated. So they are failed to be reconstructed as 2 isolated photons. So they will look like jet. So we studied this detector level simulation. We studied this photon multiplicity versus this jet multiplicity for our golden channel. And you can see that most of the events have a 0 photon multiplicity. This is for 0.4 jet radius study. So then we have a huge QCD backgrounds, WZZ or ZZZ and TTBA, and we considered all 8 standard model background process. Actually, this WZZ cross-section is about nanoband. It's very, very huge, right? So what can you do? So let's take a closer look inside the jet, cell particles. So as you know, a jet consists of many cell particles, and we found that that can give us a valuable information about the cell particle called E-flow object, indicating whether they are E-flow electron, photon, E-flow charged hadron, or E-flow hadron. Okay, then our signal jet, right, consists of 2 E-flow photons. So this is called the diphoton jet, Then you can say, okay, now we can distinguish this diphoton jet from QCD jet, but we found that there's a obstacle, pyros. We do have about 200 pyros at the HL-LHC. And this is without pyro. This is the jet image with 25 pyros, but with 250 pyros, we have this one. So now before, okay, our dijet, diphoton jet can look like a QCD jet because of this pyro. So we need a good pyro subtraction mechanism. And we found that, in the market, there are several, pyro subtraction code, but we found that this kind of a hybrid method is very efficient. For example, you can remove charged pyro cell particles by this charged hadron subtraction, and you can remove these neutral pyro particles by soft killer. Actually, how can you demonstrate that your program hybrid method is better? So we studied jet images in 4 categories. This is total jet image. This is jet image from E-flow photons, jet image from E-flow charged hadron, E-flow neutral hadrons. Actually, this is the jet images with no pyro situation, which we aim to reproduce after pyro subtraction. And this is the jet image with 200 pyro, and then we remove that with our hybrid, method. And the final thing is the same result with soft killer only. And if you look closely, for example, E-flow charged hadron images, then and this one and this is, more similar. So we can say that now we have a better pyro subtraction program. Yeah. So we included all 200 pyro particles and we subtract that. And then we did this Kopflow analysis. So to efficiently cover the entire allowed particle space, we considered 18 benchmark points. And what are the characteristics of our signal? As I said, our signal jet is a diphoton jet, so the leading and sub-leading cell particles should be E-flow photons, right? So we studied this, tagging and mistaking probability of this diphoton jet. These are for the signal process benchmark 1, 7, and 13, and this tagging probability or tagging efficiency are pretty good, at least 50%, or something like 80 or 80%, something like that. What about your mistaking probability of a QCD jet to be tagged as a diphoton jet? It's only a few percent. This is very good. Another thing is that, our signal has only two photons, right? So these 2 leading cell particles will have most transverse momentum of this model jet. So we considered this so-called PT ratio of the cell particle to mother particles PT. And this is a signal, red our signal. And you can see that this is log plot. So your signal has much larger this peak ratio. So, okay. So these are our cut floor, I'll be quick. This is our basic selection. So we imposed this series of, peak ratio cut, and we calculated this uncertainty. The significance with 10% uncertainty, but unfortunately, the significance is not that high. But if you impose this tagging, Diphoton tagging efficiency, then your significance is huge, like 22.8, something like that. What about the other all 18, benchmark point? They all enjoy very large significance. Actually, most of them have more than 5 square. But you may wonder why we didn't impose mass condition, right? Because there are two masses to be reconstructed. One is this fermiophobic Higgs boson mass through this invariant mass of 2, diphoton. Okay, and the other one is this charged Higgs boson mass through this transverse mass of this system, right? But actually, there's a big obstacle because this is not because of the signal. This is because of the background. Because in order to have this nice distribution of the background distribution, without background distribution, we cannot tell anything, right? But the problem is like this one. Because in simulation, we need a certain number of, substantial number of background events. The problem is that we generated WZZ background events, like 5 times 10 to 8. That was maximum with our computing power. But after imposing all the cut, only 51 events remain. And what about ZZZ? Out of 5 times 10 to 7, only 4 events. Then you cannot have reliable background distribution. So we devised a new method called weighting factor method. So this is the conventional way to calculate your cut-based analysis for final the cross-section after the final selection, right? You just select the events satisfying the final selection, right? And you count this like this, right? So this is kind of a binary selection, live or dead, right? In this weighting factor method, we consider a larger set. Right? For example, you consider the events satisfying this level. After that, we will impose this tagging efficiency, right? So we will consider this tagging efficiency as a weighting factor. In this way, you don't kill the background event completely. So you have some backgrounds with events with partial survival rate, something like that. Then you can have this very nice smooth background distribution, and of course you can see very nice bumping. This is the invariant mass of 2 subparticle photons, right? So you can see very nice invariant mass peak for the signal, and of course this is after the final selection, and this is the transverse mass distribution. And for this ZZZ and WZZ background, and for benchmark point 7, 10, and 12, and 6, then actually this position is very similar to charged Higgs boson mass. So I'll tell you briefly about our machine learning techniques. We did this because actually this part, benchmark 6 and 12 and 18, they have relatively moderate significance because they have heavy charged Higgs boson case. So this is our machine learning architecture, which actually this is quite simple machine learning. We have this one-dimensional CNN and MLP1 and MLP2. Maybe this is not so interesting. So we did that, and with this machine learning technique, we could before, let me see. So here, before, the significance was 477, something like that. But with this machine learning technique, we could enhance the significance like 18 or 33, 32. So as I said, we covered all the viable parameter points. And if you look at, if this is the model of the nature, then we could see this at the high luminous LHC for the entire viable parameter points. So thank you. I'll stop here.
Thank you very much. Good morning. It's a pleasure to be here in Paris. So what I'm going to talk today is about some exotic scenario with cosmic matter-antimatter separation, and I will discuss why cosmic matter-antimatter separation may be relevant for sterile neutrino dark matter. But just to say a few words about sterile neutrino dark matter, perhaps the simplest minimal model of new physics, which explains simultaneously dark matter, baryon asymmetry of the universe, and neutrino masses, is this one. We call it nu-SAM, and it's a complement of the standard model by three right-handed neutrinos, or use the particle data name for it by three heavy neutral leptons. So this heavy neutral leptons provide candidate for that matter. They explain all experiments in neutrino physics. They explain baryon asymmetry of the universe. So if this model is right, you shouldn't see anything at LHC new. Okay. Perhaps there is some little part of parameter space which you're gonna see at high luminosity upgrade. Not anything else. So let me tell you what are the roles of HL in this model. The lightest one is a dark matter candidate, whereas two others are responsible for neutrino masses and barogenesis. My focus here is on dark matter, and here we will see why I'm talking at all about QCD phase of the standard model. So we have HL is embedded in the standard model in this way. It interacts with the Higgs boson through Eucharia interactions, and for it to be a dark matter particle, it should have a lifetime larger than that of the universe. Okay, it can decay through the mixing. So this is HL, mixed with neutrino, Z, nu. So this lifetime must be greater than the lifetime of the universe. In addition to that, the same particle can decay radiatively, again, mixing, neutrino. Here you split at charged particles. You attach photons to the charged particle, and you get two-body decay with some width, and you can search for this type decays if you use X-ray telescope in space, such as Chandra, X-ray Newton, etc. Here is the account for different constraints on this particle. This axis is the mixing angle with ordinary neutrino. This is the mass, and then there are plenty of different lines. Some of these lines are model independent, some of these lines are model dependent. So for instance, this part here, it is forbidden by X-ray observations. This part here is also model independent, and it comes from dwarfed spheroidals. Now, if this particle is created in some way, then these constraints can be enhanced, and then the mass which is allowed for this particle moves in the right direction. There is a suspicious line here, 3.5 keV line, which would correspond to decay of 7 keV right-handed neutron. Okay, so if we think how these particles would have been created in the early universe, there are different possibilities, and the simplest and perhaps the most economical one would be that it is created by the same type of processes, namely the mixing with the ordinary neutrinos. And then the diagram which I showed to you, which leads to decay of this particle, is also leads to its production. We have neutrino in initial state, boson, mixing, you get neutrino. The same with W. Now, if you do a computation, surprise, you will find out that the temperature of production of dark matter neutrino is about 100 megaelectron volt, 200 megaelectron volt, depending on the mass of this particle. So this is a game of numbers. LCD physics is not involved in derivation of this number. It just happens this way that the temperature at which these guys are produced are associated with the QCD epoch, and this is the reason why we'll be talking about QCD phase transition. So there are several kinematics regimes in which right-handed neutrino production takes place. So the first one goes under the name Dodelson's withdrawal mechanism, and it's simply the graph which I showed to you. Okay, and if you and this mechanism works if the universe is symmetric with respect to lepton number. So there is no lepton asymmetry. Lepton asymmetry is very small, and this mechanism is excluded by now because it would correspond to this line on this plot. Here, everything is forbidden by X-ray observations. There is a part which is not forbidden by X-ray observations, but since we know the momentum of sterile neutrino, we can run that through structure formation constraints, and then we see that it doesn't work. There is yet another possibility which goes under the name Fuller mechanism, and which exploits the fact that the dispersion relation of active neutrino changes. Okay, and it changes in the following way. If this red line corresponds to dependence of energy on momentum for sterile neutrino, and blue line correspond to active. When you have lepton asymmetry, this blue line, it moves in this orthogonal direction. And then you see that at some stage there can be a crossing between these two lines, and that this means that the production of sterile neutrino enhances. And it enhances and it opens the part of the phase space which is not allowed, which was not allowed if the lepton asymmetry is absent. Okay, so somewhere here we can get enough dark matter particles. And also what is interesting is that the momentum of sterile neutrino is smaller than in the previous case, and this means that the structure formation constraints are less severe. Okay, so if you say, okay, suppose that this is the final model of low energy universe up to the Planck scale, say, then the question arises, can the lepton asymmetry be created also in this model? Okay, baryon asymmetry can be created, but in order to have enhanced dark matter production, we also need large lepton asymmetry. So the answer is yes, potentially yes, because what happens is that when the universe evolves, you first produce baryon asymmetry, but the production of baryon asymmetry finishes at temperature 130 GeV, and this is the temperature at which Fuller-on transitions are switched away. But non-equilibrium still continues, the lepton asymmetry can be produced, and so these two numbers, lepton asymmetry and baryon asymmetry, are in general decoupled. And so the large lepton asymmetry can be produced as well. However, there is some price to pay. For that, one needs some strong degeneracy between heavy neutral leptons. Okay, maybe that's okay, but this sounds unusual. So let me now come to the point. All previous studies of matter production were based on the assumption, that sounds as a very, very natural assumption, that the universe is absolutely homogeneous and distribution of lepton number, it is homogeneous at temperatures of dark matter production, so at QCD. Okay, this is very, very reasonable assumption, but this is still an assumption. And it may be very well that the universe is inhomogeneous at small scales at the QCD. So the reasons of this homogeneous can be many. Okay, there could be magnetic fields, other things. The point is that the universe doesn't remember several things. So for instance, you can say, okay, there are constraints on homogeneity of the universe at BBM. Okay, BBM is 4 mega electron volt. And here, the temperature is 100. And there is a lot of time here. And even if you have it homogeneous at the QCD scale, then this inhomogeneities will be smeared away by different processes, such as neutron diffusion. Okay, so what Alexei and I decided to look at is suppose that there is a first order QCD phase transition. Okay, so one can say, well, there is evidence that there is a smooth crossover, but evidence is not approved yet. And in my mind, the existence of a very weakly first order phase transition is not still ruled out by lattice simulation. So what I'm going to do, so I assume that there is QCD phase transition. And let's see whether QCD phase transition may change something in our analysis of dark matter production. So if there were QCD phase transition, then this is a spectacular event. And the people were fascinated by that a long time ago. Diphoton wrote a paper on cosmic separation of phases, and there were many people involved in that. Mikhail, many. Then this is a very interesting process. It occurs in the following way. So first, you get nucleation of hadronic phase, okay, and then this hadronic phase, and then the universe is kept at the constant temperature, okay, like boiling water in the deep. The universe expands, the temperature kept constant, and the droplets of a new phase, hadron phase, they expand, and at some stage, you get an inverse situation. The whole universe is in hadronic phase, whereas there are droplets of quark-gluon plasma. Okay, and Witten and others argued that this process, it would lead to the concentration of baryon number here, so that the baryon number is swept up by the bubble walls. It is resting in quark-gluon plasma, so you have here an excessive baryon number, and here baryon number is well, almost zero. You can do an estimate, and you see this is harmless for BBM. The size of these guys are sufficiently small, and they are dissipated by the time of BBM. So why this is interesting for cell neutrino production? Because of the following reason. As I told you, the probability of cell neutrino production depends on the symmetries, and in particular, it depends on baryons. And so if you squeeze the baryon number in one place, then the production of magnetic stereo neutrino in these domains is enhanced. Okay? And moreover, since the universe can potentially contain lepton asymmetry, which is much larger than the baryon asymmetry because of decays of H and L's, not only that, then the dynamics of this bubble can lead to creation temporary creation of matter-antimatter domains. So inside the bubbles, you get matter. Outside the bubbles, you get antimatter. That doesn't lead to any baryon asymmetry because it will be smeared out later on. But this can be the case. One can even discuss even very, very exotic possibility, very speculative, which was discussed and proposed in a different context by Omnes back in '69, when he tried to explain baryon asymmetry universe by separating matter and antimatter. This doesn't work, but something similar can occur here. It can depend on the QCD dynamics. So if that would be right, then two types of bubbles will be created, one with positive baryon number, another with negative, and then it will be all annihilated at the end of the QCD phase transition. Okay, so now what can be done? So you take this inhomogeneous picture with excess of matter in one place, excess of antimatter in one domain, and then you can repeat the computation of dark matter creation. How much time do I have?
You have 2.5 minutes.
Okay, so there are two cases which can be considered: large droplets, larger than the mean free path; small droplets smaller than the mean free path. One can do this analysis. You have some integrals, so you have to integrate to get the baryon asymmetry. So if you do this computation, which is still subject to a number of uncertainties because it depends on dynamics of the phase transition. So maybe there is no phase transition, then it doesn't work at all. Then maybe it will work if there are inhomogeneities created by some other QCT case that wouldn't work. But what we see is that, yes, if such inhomogeneous situation did exist, then we can get efficient production of dark matter, even if the mixing angle of these particles is well below the values which are indicated by X-rays. Okay, because resonance is enhanced in this domain. Another thing which is very interesting is that since you can get, you can have large asymmetries, and large asymmetries means that neutrinos are created with smaller momentum. And you can get even momentum which would make this particle do its life, the cold dark matter candidate, so that all the constraints coming from, say, Lyman alpha forest or from draft spheroids can be evaded. And yet another interesting thing is that we can get enough dark matter even for asymmetries smaller that you need to get correct dark matter abundance for homogeneous situation. And this may have some relationship to fixing the mass of heavier HNLs which produce lepton asymmetry. So let me show you this picture. This is the green stuff is the lepton asymmetry which can be created in the case of heavy HNLs. This is their mass, and this is the asymmetry. So this line here is the necessary amount which is needed to get right dark matter abundance, homogeneous situation. And if you do a computation, so this green thing is you vary the parameters of the model and you see how big a symmetry you can create. Okay, so you see that it doesn't go this way, unless there is fine tuning, which I'm not discussing. Now, in homogeneous situation, we don't need so big a symmetry. We need a symmetry like this. And here you see an interesting thing, that this can be only achieved by HL masses which are below certain value. And these certain values few cheap electron volts. And this is kind of the first phenomenological indication of their mass. So I'm coming to my conclusions. If the first order QCD phase transition took place, then the sterile neutrino dark matter production can be enhanced due to temporal matter-antimatter separation. So the last statement is true for other mechanisms of producing energy, which may also take place. Depending on the nature of transition, the required lepton asymmetry can be smaller than in the homogeneous situation. These asymmetries can be produced at the freeze out of heavy HNLs without fine-tuning if their mass is below GeV, and perhaps future experiments can find HNL. Prism in space, which was launched in September last year and shipped at CERN, which was accepted in March 2020.
All right. Good morning, everyone. First of all, thanks to Venus for the very nice invitation to come to Ireland for the first time. The title of my talk is Two Ideas About Dark Matter Model Building, but Venus is notoriously tough. She reminded us of that this morning, and when she reduced our time by 5 minutes, I also had to change the title of my talk. So in fact, that's a pretty stupid title. I'm going to be talking about one aspect of dark matter model building.
Just for that joke, you get an extra 5 minutes.
Thank you. I'm after extra prizes. All right. So, what problem are we trying to solve in this scenario? Well, it's a cosmological coincidence problem. It is now very well established that the dark matter density in the universe today is rather similar to the baryon density, mass density in the universe today. They differ by about a factor of 5, which is not a large number in the cosmological context. And to me, this is a piece of evidence, piece of empirical evidence that may point to the underlying nature of dark matter, or at least it is worth exploring the possibility that this is not just a weird coincidence, but in fact that there's something deep behind this observation. Anyway, let's take this observation seriously as a hint for the nature of dark matter, and we don't have too many hints about what the nature of the dark matter is. So let's take this seriously. All right, so a mass density is the product of a number density and a mass. So here is the coincidence expanded out. Now, I think the main paradigm, there are other ideas out there as well, but the main paradigm that has been looked at for addressing this coincidence is asymmetric dark matter models. And these were very popular around a dozen years ago, and maybe 200 or 300 papers were written. And if you look at those 200 or 300 papers, what they all do is produce a scenario where the number densities of dark matter and baryons come out to be similar. They don't have to be identical, but related in some ways through some chemical reprocessing scenario. But if that's all you do, then in fact you're not explaining this coincidence, because you also are missing an explanation of why the dark matter mass scale should be related to this weird thing, which is the proton mass scale. And indeed, in most of these 200 or 300 papers, they take this coincidence as a way to predict what the dark matter mass should be. And that simply moves the coincidence from the cosmological domain to why the dark matter mass should have anything to do with the proton mass. All right. And so what I want to talk to you about today is an idea about addressing this problem in the context of asymmetric dark matter. Here are the relevant papers. So it was started by Bayern Schwaller some 10 or more years ago. There was a follow-up paper by Newstead and Tabik. And then with my PhD student, Alex Ritter, I've written a couple of papers on the topic. And most of the time in this talk, I'll be talking about our latest paper just produced last week. All right, so here's the framework. So the proton mass which figures in our narrative, is set by lambda QCD. Not set by Higgs or anything, it's set by lambda QCD. It's set by strong interactions. So that being the case, how could it be that that's got anything to do with the dark matter mass scale or dark matter at all? Well, it could be because, and many people have looked at this for various reasons, it could be that there's a dark QCD, that there's a strongly interacting asymptotically free gauge force in the dark sector, and we have dark baryons, and it is the confinement scale of dark QCD that sets their mass scale and hence the dark matter mass scale. So what we're after is a dark QCD model where the confinement scales of ordinary and dark QCD are similar to each other. Don't have to be the same, but similar to each other. So if you think about how you might approach getting such a scenario, there are, I think, two approaches only that have been suggested in the literature thus far. It'd be interesting if there were others. One of them is an obvious one. It's a symmetry approach. Maybe there's some symmetry that interchanges ordinary and dark QCD, and you're led pretty quickly to a mirror matter type of model, which I have investigated in the past, but I'm not going to talk about that here. Instead, I'm going to talk about an alternative idea which doesn't rely on a discrete symmetry between the two strongly interacting sectors, and perhaps gives one more freedom in model building. And in any case, is just a different idea to explore. It's based on infrared fixed points. All right, and this is the idea that was proposed by Yang Bai and Pedro Schwaller more than 10 years ago. So here is how it goes. The horizontal axis is energy, and the vertical axis is the value of the two strong coupling constants, the ordinary one alpha S and the dark one alpha D. So the idea is that you want to engineer things so that you have a fixed point in the infrared. So as you evolve down from the Planck scale, from some UV scale, you hit an infrared fixed point where the beta functions for both the dark and the ordinary QCD coupling constants vanish. And we'll denote the coupling constants where that happens with a star. And the idea is you engineer the particle content above this scale of new physics M to have these fixed points such that when the new physics decouples and these things start to run simply on the basis of gluons and dark gluons and whatever light dark quarks there are, that you get confinement scales in the end that are within some range that you deem acceptable as an explanation for this correlation between the dark matter mass scale and the proton mass scale. So that's the idea. And the beauty of these infrared fixed points is that then there's complete insensitivity to whatever the coupling constants are in the deep UV at the Planck scale. They could be anything at all. I mean, we maintain perturbativity so that we can do the calculation, but otherwise the coupling constants could be anything, and it doesn't matter. They still evolve to the same point. And so even without a symmetry between the two QCDs, you get some relation between the confinement scales at low energy. So I thought that was an interesting idea. Okay, so it's a nice idea, but there are some issues. And in my first paper with Alex Ritter, we explored that idea and critically examined it and decided there were some issues. First of all, this is the formula for the values of the two coupling constants in terms of beta function parameters to get the fixed point in the way that Bai and Schwaller suggested. And it requires a conspiracy between particle content that under, you have new particles that are just have ordinary color, others that just have dark color, and then others that are colored under both sectors. And you need a conspiracy to even have an infrared fixed point at finite values of these coupling constants. So you can find such models. Bai and Schwaller produced a few. We produced a few more, but they are non-generic. Secondly, you don't actually get to the fixed point, even if you evolve all the way down from the Planck scale. This is the first thing we noticed. Here is a grid of points in the deep UV, just initial values for the two coupling constants. Here's the infrared fixed point, and you see that after you've evolved, you approach the fixed point, but you don't reach it. And that means that there's remains some sensitivity to the UV values, and this reduces the successful parameter space, because for some of these points, the two confinement scales will be too different to be deemed acceptable. Okay, and the other thing we saw when we did a survey of all of these different kinds of models is that the mass scale of new physics that you need is typically rather light. So here, what we have are the two blue lines, and between the two blue lines is deemed the acceptable region. So we've taken that lambda dark QCD should be within a factor of 5 of ordinary QCD in order to get the dark matter mass scale suitably related. So we want to be within this regime, and the area here defines, if you like, the success of the model. So if you're outside these blue lines, it's an unsuccessful model. You haven't related the confinement scale sufficiently. Now, these purple lines are scales of new physics, and you can see that most of this acceptable parameter space has new physics, strongly coupled new physics, ordinary QCD strongly coupled new physics below 1 TeV, and that's excluded. So although you're allowed this sort of relatively large region, only this little bit is actually phenomenologically acceptable. And so that reduces the success of this scenario. This can be fixed, but we found it could be fixed in a very contrived way by having very large multiplicities for fields in fundamental representations. Numbers like 17, came up, and that looked a little contrived, so we weren't completely happy with it, although we could engineer it to happen. Thank you. Okay, so what we've done in our new paper is to look at an alternative to the Weierstrass idea. So what they propose that is the infrared fixed point is at finite values of the couplings. But if you solve beta functions being 0 and look at all the possible solutions, you get these 4 solutions. And in our new paper, we instead exploit this one. There is always a fixed point when the 2 alphas are 0. It needn't be an infrared fixed point. Sometimes it will be, but it is at least a fixed point. In order to have this as an infrared fixed point, we need the 2 QCDs to be non-asymptotically free above the scale of new physics m, but we do require that things remain perturbative up to the Planck scale so that we know what we're talking about. We're also going to allow for higher dimensional representations, which we didn't do in our earlier work, and that's in order to have running be faster if that's what we need. And we're also going to deviate from dark QCD necessarily being SU3. We also explored SU2 and SU4 as well as SU3. All right, and the attraction of this is that many models have what we call a 0 coupling infrared fixed point, so the scenario is more generic. If you have higher dimensional representations, then you need lower field multiplicities because the group theoretic factors are bigger and the running is stronger, so you don't need to just add more copies of the field in order to get the stronger running. But having the stronger running having the stronger running above the scale of new physics means the scale of new physics can be made higher and we avoid the phenomenological problem. There are also some disadvantages. Having m very high leads to a naturalness problem, and having a very high m makes the new physics hard to find experimentally, although there is the possibility for detectable gravity waves from the dark QCD phase transitions. All right, so let me show you some results from our analysis. Firstly, we'll go to a non-supersymmetric framework where we abide by electroweak naturalness constraints. We're trying to explain a cosmological coincidence, and I don't want to do that in the framework of theories that have other fine-tuning problems. That would be not the right thing to do. So we have to make sure that we don't introduce a naturalness problem, and this gives us upper bounds on the scale of new physics, depending on what type of exotics we hypothesize. So this scenario can be made to work, but it is not generic, and we're after something, hopefully, that is more generic. I want to introduce some terminology. We have this thing called the viability fraction, epsilon v. It's what I explained before. It's the area between the 2 blue lines, which is deemed to be the successful area. And then in this case, we also have this thing, epsilon v10, where 10 stands for 10 TeV. So this is the fraction of acceptable parameter space where the scale of new physics is less than 10 TeV, and therefore we don't introduce a naturalness problem. And you can find scenarios where this viability fraction without there also being a naturalness problem is about a quarter. You know, you can engineer scenarios where that happens. And so this is kind of okay. It means that the cosmological coincidence has been reduced to a 1 in 4 chance rather than like a 1 in a million chance or whatever it was before. So it can be done, but it's non-generic. It needs some finagling in terms of what exotics you put in and so on. Okay, so the reason that was very constrained was the desire to have the scale of new physics relatively low. If we want to expand our possibilities, we need to have the scale of new physics higher, or admit possibilities that they are higher. As soon as you do that, you run into a naturalness problem unless you invoke supersymmetry. So we were kind of forced to invoke supersymmetry in order to explore these more generic scenarios. And here I want to show you some results. First of all, the results depend strongly on how many light-dark quarks there are. So you have to imagine that we have new physics at very high mass scales, above big M, very high mass scales, but then we also need one or more light-dark quarks, because those are the things that are going to be bound into our dark matter candidate, which is a dark baryon. All right, and it turns out that the results for this viability fraction depend strongly on the number of light-dark quarks, and you see for this particular example, I won't explain all of this. You get a sweet spot at 6 light-dark quarks where this area is maximized. All right, so it's just a relevant parameter, the number of light-dark quarks. Let me show you the results for supersymmetric dark SU3. Here we have a plot of the viability fraction as a function of light-dark quarks with varying exotic particle content. That's what all these little dots means. They're all different models with varying exotic particle content, heavy stuff above the new mass scale big M, and with the number of light-dark quarks being a variable. And you see that you can get viability fractions that are between about a quarter and about a third in this particular case. And here are some examples where that happens, where we change the number of light-dark quarks from 1 up to 8, all right, which is what is on this horizontal axis. And you see that the viability fractions in this particular scenario, which is some particular choice of exotic particle content, goes up from 0.26 to 0.35 as we increase the number of light-dark quarks. And we find in our survey that about 40% of models have a 1 in 4 chance of having explained the coincidence in some reasonable way. When we move to dark SU4, actually the situation is better, which is interesting. Here is a similar plot. Number of light-dark quarks is possibly getting a little high, 10 or 11. Nevertheless, that's what we looked at. And in this case, we find that you can get viability fractions up to more than 0.4, so getting up to about a 1 in 2 chance that the dark matter coincidence is explained. And we find here that about 65% of the models, successful models, have a viability fraction above about a third. And SU2 doesn't work very well. Very few models have a decent viability fraction. How much time do I have?
You have minutes.
Okay. All right. So our analysis was not about, a lot of it was not about complete models. It was just throw in some exotic particle content, look at what you get for the relationship between ordinary QCD confinement scale and dark QCD confinement scale, and do you get the confinement scales in the range that is reasonable for a successful asymmetric dark matter model. But that is just the bare bones. It's the foundation for building a complete model. So there's a lot of work to be done if you want to take this seriously, starting with results such as ours and trying to write down a complete theory. So you want an asymmetry generation mechanism that relates the asymmetries in the ordinary and the dark sectors. You want the full dynamics of all of that. You want the CP violation. You want everything like this. So what we did in our paper was make a start on that. We took an SU4 supersymmetric model because these are the ones that seem to work the best. for explaining the cosmological coincidence. And we looked at superfield content within those theories that permitted a successful asymmetry generation mechanism in both sectors via leptogenesis and reprocessing. And we found examples of that. We found examples of theories which have a high viability fraction, meaning the cosmological coincidence has been ameliorated to quite a large extent, that also have the correct particle content to be able to give us asymmetry generation in both sectors that is also that also looks successful. So this is a sketch. The detailed model building is still in its infancy. Okay, so let me conclude now. So I think this infrared fixed point idea introduced by and Schwaller is a good one. Our new proposal that you use the zero coupling infrared fixed point permits more generic models, that's for sure, and has some improved features. They seem to work somewhat better. Whether I like it or not, supersymmetry is relevant to avoid a naturalness issue with this new high physics scale. SU4 as dark UCD seems to be better than SU3, and SU2 doesn't work very well at all. And there are interesting cases that have the prospect of being used as the basis for complete theories. I didn't talk about it much, but a kind of generic prediction of all of these dark QCD models, which have a first order phase transition, is a stochastic gravity wave signal. And in fact, I wanted to ask Michel if he has a prediction for a gravity wave signal in his scenario. So that's probably a good way this is probably the best way to search in a generic sense for a dark sector that contains a QCD like gauge force and where the dark matter is a dark baryon. And as I said, the model building has only just begun. Thank you.
Thank you. So, good morning. Thank you for the invitation. It's nice to be here. Nice to see some friends. So, this is the topic of my talk. It's based on this work, something I wanted to finish but for the conference, but did not have time, as usual. It's about a bit dark matter abundance and it's dark matter chemistry, but as you will see, it's also about mapping dark matter candidates. So there is a sort of obsession in our field about mapping dark matter. I guess it's because we don't know what it is. And but basically, the point I wanted to address is similar to what is in this plot. Basically, what is the range of dark matter candidate? And I will focus on thermal particle, as in this figure. By this, I mean particles that were in thermal equilibrium in the early universe. So I will not consider dark matter like was considered by Michel, and I will not consider asymmetric dark matter either. So these two talks were excellent introductions. So what I do is very basic. So this is one of my favorite figure. It was done by Kimo. I think he's in the audience. Okay. Anyway, so basically it's a classic example. It's a massive neutrino, stable with weak interactions. And as you know well, there is the famous Leeuwenberg solution. Of course, that solution is excluded, but this is not my point. I want to focus on the fact that this solution stands between two extremes. These extremes corresponds to dark matter particles that basically froze out when they were relativistic. Okay. Of course, they are excluded also, but again, this is not my point. And then on the I mass range, there is the so-called Gris-Gamiankowski bond. So basically what you do is that you assume the largest possible annihilation cross-section as set by unitarity, and you get a dark matter candidate in this mass range. So I want to focus on a very basic point, which is that the things go up and at low mass and also at large mass. And so they must go down in between, and so you have a dark matter candidate by the median. So of course, that was assuming weak interactions, but if you change interactions, you can change around the position and the mass then of the candidate. So at the end of the day, you have a range, okay? And this is the usually quoted range for thermal dark matter candidate, okay? And that goes from a very light candidate, a few EV, to up to a few tens of TeV, depending on who you ask. Okay, so this is what I mean by the range. And this is for basically for thermal dark matter candidates that were in thermal equilibrium with the visible sector, that is the standard model. So, okay. So to spice up things a little bit, I will shift framework and I consider hidden sector framework. So basically, you're all familiar with that. This is hidden and it contains dark matter. This is visible. So basically, you assume that you have a singlet dark matter particle in this sector. They may have interactions and they may thermalize, okay? But they may thermalize at a temperature that doesn't have to be the same as the temperature of the visible sector. And that's an extra degree of freedom that you can use and play with, okay? And then, of course, at some point, you may have a portal. Usually, this portal is assumed to be feeble. I will start by assuming that there is no portal. So really secluded hidden sector. So how you can get a different temperature? Well, perhaps there was something like asymmetric inflation. I will start with something simple and mundane, which is let's assume that T prime, the temperature of the hidden sector, is less than that of the visible sector. Is there a timer or something? It's your watch, yes, okay. Yes, anyway, give me 5 minutes before the warning, before the end. Thank you so much. Yes, it's kind. So how this very simple picture changes if you lower the temperature? Well, on the lower mass edge, it's very easy because it's basically proportional to the abundance of the dark matter. So if it's suppressed by a temperature, you get something that scales like that, okay? So the solution moves toward the right. What happens at the heavy mass range, you know, this is just ordinary freeze-out, is not altogether obvious, but you can work out things. The abundance is set by T prime, but the expansion is set by T, the temperature of the visible sector. And so you work out things and you get something that scales like that. So you get to the following picture. So it's a very simple plot. So it's the mass of the dark matter, the ratio of the temperature, and to begin with, I focus on the cold dark sector. So that boundary is basically the extrapolation to low temperature of what you have for the small mass range. So basically, there are dark matter particles that froze out when they are relativistic. Okay, if you stand in the blue region, you are under abundant for a given temperature ratio. If you stand here, the particle is under abundant, so you must be above or along the line. And that boundary is the extrapolation of the Gries-Kaminkowski unitarity bond toward the low temperature. And again, you use basically this scaling. It's interesting that they don't scale quite the same way. So basically, the curves, they meet at a point. And so there is sort of lower temperature in this picture that corresponds to a temperature of the visible sector, which is much higher, which is of the order of 10 to the 11 GeV. In that picture, it's a very cold hidden sector. Dark matter froze out when the temperature of the visible sector was quite large, 10 to the 11 GeV. And you know, you go beyond the usual coated mass for the unitarity bond. Okay, so there are some extra details in this plot, but I gave some comments so you can read by yourself afterward or never. In principle, so this is sort of a generic range. So, you know, then you can look at specific dark matter candidates and look at how they fit in. I will focus on a very simple model. It's sometimes called a dark QED. So basically you have dark fermions and you have a dark photon, and I will assume that the dark photon is massive, as is often the case. So it's basically a 3-parameter scenario, and on top of that, I have the temperature. And then you can work out the abundance, and you get, of course, the abundance in this case is set by the interaction of the dark fermions with the dark photons. And in particular, if we consider non-relativistic freeze-out, you have this kind of diagram. So it's very basic. And so, you know, basically, what you get is extrapolations, but within for finite couplings, basically, of what you have on the boundaries. Okay. So different solutions, and they depend on your choice of the fine structure constant. Okay, so let me go now to something more unusual, which is basically by continuity of this region, you can go now and imagine that perhaps the dark sector is actually hotter than the visible sector. Of course, something we cannot live with today, okay, because obviously our universe is dominated by, well, of course there is dark matter, dark energy and all that, but you know that, of course, for instance, by the time of BBN, we know for sure that the expansion was driven by the known degrees of freedom of the standard model. Okay, but let's see basically what happens in that region. Basically, you have by continuity, you have extrapolation of the Grieskamp-Minkowski bond. The fact that it becomes vertical is essentially because the expansion and the freeze-out, everything is set by the temperature of the hidden sector. So it's independent of the temperature of the visible sector, at least at this level. And then that constraint is a very basic and stupid constraint. We are just asking that there are not too many of this stuff by the time of BBN. So, and that's set by the so-called delta NF constraint. So you get this white region. And, but of course, it's a bit tricky, because it's a situation where in the past there was a lot of heat, energy, entropy, whatever you call it, in the hidden sector. And the problem is that dark matter, of course, I mean, here I'm assuming that dark matter, for instance, is annihilating into lighter particles. This is what you need to have freeze-out and things like that. And of course, after dark matter freeze-out, you have a lot of these light particles that hang around. We call them companions, etc. You can call them dragons if you want. So to be specific, if you have in mind the dark QED scenario, there are a lot of dark photons floating around after dark matter freeze-out. 10 minutes left? Oh, that's mean. Okay, I'm going too fast. Well, anyway. I win a prize if I slow down.
No. If you buy us some time, that's perfect.
Okay.
Any questions?
Yes. Okay. Well, I have a few points about that, but okay. But thank you for the.
Sure.
Yeah, I'm very confused with this competition game. So the rule is really to go quick. Okay, go.
To be on time.
Yeah, sorry, but I lost track of my talk now. So dragons. Okay, so we were speaking of dragons. Sorry, I'm losing time. Yes, very good. Yeah, okay. So what is the problem? I guess you got the issue here. Is basically that perhaps there was inflation, and but perhaps the inflation heated more the hidden sector. So there is a lot of entropy here. We want to set up the dark matter abundance through secluded freeze-out. Well, I use a secluded freeze-out as a generic name. But then we need to get rid of the entropy. So basically, we need to reheat the visible sector. So it's a reheating problem. Okay. In brief, it's a weird indirect reheating of the standard model sector. Instead of having reheating of the visible sector at the scale of inflation, we go in 2 steps. Okay, and see what we learn and if we learn anything. So, of course, to get rid of the entropy, we need a connection, so we need a portal. So, building up on what I've just said, I will use the standard portal for dark QED, which is kinetic mixing. So, basically, there is mixing between the dark photon and ordinary photon, and so we can have exchange of energy between the 2 sectors. And the dark photon is still massive. So basically, you work out the different process, but the relevant process, most relevant process at the end of the day, is decay and inverse decay of the dark photon. And this is, how it scales. Basically, it's controlled by the mixing parameter. So it's not a very complicated problem, but it can be a little bit nasty. So we made a lot of simplifications. But at the end of the day, we want to track the abundance of the dark photon after dark matter frees out. But also we want to know how the energy is transferred. And it's not quite the same thing. And so, and at the end of the day, how the energy of the visible sector is evolving. And you write the Boltzmann equation using the usual fluid approximation, and you get funny Bessel functions. But at the end of the day, the only thing they take into account is the fact that if the dark photon is relativistic, its decay rate is less than its phase frame. So you have a time dilation basically at larger temperature than the mass of the dark photon. And then you solve the Boltzmann equation, and there are two situations. So it's a bit messy, this plot, but basically this is the scale factor. This is some arbitrary scale, and this parameter is the ratio of temperature. So we start with a large temperature ratio. So basically the two universe, hidden and visible, evolve in parallel. At some point there will be the beginning of energy transfer, and then they will thermalize. So in this situation, the dark photon basically transfers all its energy when it's still relativistic. So we call that relativistic reheating. You cannot see it because I'm sharing a screen here. But it's basically what we call relativistic reheating. There are a lot of gory details about what is going on, etc. But at the end of the day, it's very easy. I mean, the dark photon decays, it's rare, but there are a lot of the dark photons. And so eventually, even though the decay are rare, they will preheat the visible sector. And once they've reached, they've transferred most of the energy, basically they thermalize. So the visible sector and the dark sector, that is here, the dark photon, they just thermalize. And then the dark photon, they just track equilibrium abundance. And eventually, when they become non-relativistic, they become Boltzmann suppressed, etc. An important key feature is the fact that, of course, this reheating process is an irreversible process. So there will be entropy production. But in this scenario, the entropy production is mild. It's basically scaling like the fourth root of the relative number of degrees freedom that you have in the visible and hidden sector. So for instance, if you take just dark photons, massive dark photons, it's 3, thank you. But if you imagine that you have perhaps hundreds of degrees of freedom in the standard model, so basically the fourth root of that number is the other one. So it's no big deal. You have a bit of entropy production. Things are quite different if along the process of reheating, the dark photon becomes non-relativistic. So basically, you got the point. We get into a situation in which the universe becomes matter-dominated. And then it's a textbook problem, basically, to solve this. And you have, you open Kolb and Turner. They are not in the room, but okay. They could have been here. I don't know if they're your friends. But okay, anyway, it's a textbook problem. And one of the most important things you learn from this textbook discussion is that you may have a lot of entropy production. It's quite nice, actually. It's something I did not realize, but basically the entropy you produce, so you compare the initial entropy to the final entropy, it basically scales like the square root of the lifetime of here, for instance, the dark photon, over the moment when the dark photon becomes non-relativistic. So it's a very simple expression, a bit simpler than what I usually see. Anyway, a lot of stuff in this plot, but let me go forward. So we studied that in big details. I got obsessed by the scaling of the different parameters, etc., a bit like in the textbook of Kolb and Turner, 13/8 evolution, etc., Not very important. But one message that we may get is that of course, if there is entropy production, it's going to affect the abundance of the dark matter. Okay, so there's something we need to track. Okay, so what are the consequences? Well, first we can look at the parameter space of the dark photon. So this is the kinetic mixing parameter. This is the mass of the dark photon. Basically, if the kinetic mixing is too large, then you would have thermalization right away of the two sectors. It's not very interesting. I want to have the two sectors to evolve independently, at least in the beginning. And then, of course, we want the dark photon to decay before BBN. That's a mundane constraint. And so, and also, I assume that the dark photon is lighter than the dark matter. And so you have the white range here, but it can move to the right, sort of a quantum that can move. And then, you know, I told you that there are two ways to read the visible sector, either through relativistic decay of the dark photon, and that happens in this region. Of course, there are constraints here, but no surprise, we are actually discussing about some basically uncharted, unconstrained parameter space. And for lower mixing parameter, decay happens later, and then no surprise, it can happen when the dark photon is non-relativistic. So let's see now what are the consequences for the plot I showed you before. So you may recognize this funny corner, the region I showed you before. This is called hidden sector, but I want to focus on the hot hidden sector. And initially I thought that we could shrink that region to nothing because of the issue of heating, etc. But it's not quite the opposite. Actually, it opens up. And that's just because entropy production can dilute the dark matter abundance. And then the rule of the game is a bit to see how far you can push the borders. And if you really push things to the extreme, then that constraint which comes from, you know, mundane unitarity bond, etc., can move all the way up to 10 to the 11 GeV for the mass of the dark matter. So these are dark matter particles that will basically freeze out through the usual basic freeze-out mechanism, with perhaps the largest allowed reduction by, set by unitarity. 1 minute, very good. And then you get to that. But of course, these are extreme, and so you have to think that realistic candidates, they live more, you know, inside of that region than to the extremes. I basically illustrated everything using dark photons. You can look at the different curves that you get at different kind of couplings, and as promised, they fill within that region. Now, okay, basically, I'm done. The last few seconds, just to mention, and it's not totally kosher to play with the hot hidden sector, because this is basically of the fact that there is a lot of entropy, and you must, you know, get rid of that, and you can't, because entropy to a large extent is conserved, or it can be even increased, so it's bad. And but it's an interesting game, I think. For instance, there is an obvious question about, for instance, the baryon asymmetry of the universe. If the baryon asymmetry is set by the visible sector, any entropy that comes from the hot sector is going to dilute the baryon asymmetry. And of course, baryon asymmetry, we know how much it is, and it cannot be larger than 1, okay, at most. I don't know if there are any realistic scenario of order 1 asymmetry in the early universe, but okay, but if we assume that the baryon asymmetry was set when the universe was still dominated by the hot hidden sector, then you have further constraints. But then, as Michel told us, the baryon asymmetry could be set at the GeV scale, and so at the end of the day, we can live with the hot sector. So these are my conclusions. Basically, it summarizes the interplay between the different game and all the parameter space is, you know, constrained or unconstrained in this kind of scenario. Voilà. Thank you for your attention.
22 years ago, we found the Higgs after, but after 48 years, we with theoretical prediction, and the value of the Higgs cluster lies in a very lucky spot. In fact, for a 50 GeV heavier Higgs, only two basic decay channels would be visible, and for a 10 GeV lightest Higgs, the WWZZ decay channels would have not been possible so far. And we already measured the coupling strength up to Higgs boson of several decay channels, and this red line shows the excellent agreement with the standard model prediction. But several important couplings, like the self-coupling of the Higgs, are very weakly constrained, or some other are yet to be measured, like the ones to the light dots. These are the pillars of the Higgs physics at colliders. The coupling to the gate W and Z are very well measured, and they will be very well measured at the luminosity and the LHC, and also the coupling to the third generation quarks. Also, with the couplings to the gluon and the photon, we can probe new particles through loops. But there are still ingredients of the standard model which are not very well settled. For example, the linear coupling of the Higgs will be measured hopefully at the luminosity with a better precision than 50%. But that means that the potential, the shape of the potential of the Higgs is not very well defined, and there is the possibility that other particles, other scalars, can contribute to this shape. The Higgs production will be the process at LHC, and it provides a unique probe of the Higgs boson self-coupling. And as I will show, it is also a sensitive probe to Jeonghyeon standard model scenarios. It is a huge challenge for LHC because of the very small cross-section. And till now, multiple Higgs decay channels are already investigated. And LHC has reached a sensitivity to exclude a production which is 2 or 3 times higher than we expected in the standard model. The Higgs is okay. Even if the Higgs was found, as we know, there are still open fundamental questions, and we also know that the standard model is a model, it's a partial description of nature, and it could be only a part of a more general theory which will manifest at energies higher than the ones explored till now. The Higgs particle itself could not be elementary, could be a composite, could be a composite particle of some underlying dynamics, strong dynamics, and in other words, these 2 lines of the standard model Lagrangian could be a window to new physics, could be a portal to a hidden world, and the Higgs is the ingredient which could explain what is going on. The Higgs is a special particle because it is responsible for giving mass to matter. That means that when the Higgs moved the minimum of the potential, it generated a phase transition, the electroweak phase transition in the universe. So the Higgs is responsible for the evolution of the universe. This electroweak phase transition starts at the bubble nucleation temperature, and what is important is that it can trigger baryogenesis. This is difficult within the standard model, so one has to explore for Jeonghyeon standard model solutions. Jeonghyeon standard models means new physics, so new fields and new dynamics. In other words, if there is new physics in the Higgs sector, we will have, of course, deviations in the Higgs couplings, and hopefully signals colliders of physics, for example, in the Higgs production. But also, this new physics can trigger a first-order electron phase transition, and under some hypotheses, this phase transition can give electroweak biogenesis and also gravitational wave signals. That means that we can have a synergy between cosmology and collider physics, and also both a future interferometers and a future colliders. And I told you, the strong electroweak phase transition can trigger biogenesis, and the electroweak phase transition starts when bubble starts to nucleate, so at the nucleation temperature. And you can have baryogenesis if the three Sakharov conditions are fulfilled. The first one is baryon number violation, then C and CP violation, and the fact that the phase transition is strong enough and it describes an outward equilibrium dynamics. And as we know, these last two, let me try, no, don't do it. The last two Sakharov conditions are not fulfilled in the standard model, because the standard model phase transition is a smooth crossover, so it's not in a irreversible transition, and there is not enough CP violation from the CKM. In other words, new physics is needed for to link baryogenesis to the electron transition. The easiest way is to have an exascalar simulator added to the standard model theory. And this is the potential that you get. And in particular, this coupling is the most important one, because it is the total interaction between the Higgs and the exascalar. With this potential, you can have describe the electroweak symmetry restoration and the electroweak symmetry breaking by following two paths. So the first one is the normal one, is the one-step phase transition, but you can also have a two-step phase transition. That means that you start at very high temperature with no vacuum expectation value for the Higgs and for the exascalar, then the exascalar gains a vector expectation value at the intermediate temperature, and after a barrier at free level is generated, and that causes a strong, very strong phase transition between the two minima. So this is a crucial ingredient to link the electroweak phase transition to baryogenesis. And what we did is to try to realize this mechanism in a composite scenario in which the strong dynamics form composite states, and you can describe the Higgs and also this exascalar like pseudo-random Boston boson related to the spontaneous breaking, in this case of SO6 to SO5. So what we did is to construct this theory in which the Higgs and the exascalar are pseudo-random Boston boson, and study the way in which the strong, the parameters of the strong force match into the potential of the this Higgs and the exascalar, and study the way in which the electroweak phase transition can happen. This is the result in the plane of the quarter interaction coupling and the exascalar complete coupling, and you can see that you have a region in which the two-step phase transition can be realized. We also calculate the strength of the phase transition, which is the crucial parameter also for electroweak baryogenesis, and it is given by the vacuum expectation value of the Higgs at the nucleation temperature divided by the nucleation temperature itself. And this is a parameter which the value of the strength is calculated as a probability of nucleation of bubbles divided by the Hubble value. And you see that in this region, you can have this strength larger than 1, which is important for the baryogenesis. As I told you, the fact that the electron phase transition is strong first order is only one of the basic requests for baryogenesis. The other one is that you need an additional source of stimulation. What is important in these schemes is that you can have it in a natural way due to the nonlinear dynamics of the Gascon-Shotkin. So you can have operator, in this case, a dimension 5 operator, which is the coupling between the exoscalar, the Higgs, and the top. And this operator can have, this interaction can have a complex coefficient, and it induces a phases in the top mass, which becomes physical during the electroweak phase transition when eta changes its reference position. So in this way, you can have this extra source of CP violation, and we have calculated if it is sufficient for baryogenesis, and in fact it is. In the region where you have the two-step phase transition, you can also have this parameter D over F, which is enough to reproduce the asymmetry between atoms. Another bonus is that the bubbles expand, collide, and can generate a stochastic background of gravitational waves. And we have calculated the spectrum, the peak frequencies for three-dimensional points, and found that they can, they are within the sensitivity reach of the future experiments at, for example, LISA or other space-based interferometers. So hopefully we could have signals from this new physics as gravitation, as a stochastic background of gravitation. One of the parameters which is very important in this calculation is the speed of the wall of the bubble, and this has a strong effect on the shape of the power spectrum, and this can be determined by solving the Boltzmann equation, which describes the plasma dynamics and its interactions with the bubble wall. And we recently did this calculation, so we have this parameter which is better calculated with respect to the ones that we use for this analysis. In the 5 minutes left, I want to show the complementarity that I announced to you. So we consider another scheme for composite dynamics, which is the realization of a composite Higgs array model. And so we have two Higgs doublets as observed among bosons. And among the ingredients which are important in this analysis, we also consider the effect of the exascalar, which are naturally present in these schemes. These are the parameters of this composite two-tablet model: the scale of compositeness, the strong coupling, and the parameter in the Fermi-Lagrangian describing the interaction of these heavy fermions with the standard model fermions. Just to show you an example, we made a scan over the parameter space with a constraint to reconstruct the vacuum expectation value of the Higgs, the mass of the Higgs, the mass of the top, and also the bound on the heavy tops to 1.3 PeV, which is the present bound from direct searches at the LHC. And for example, you can see that still deviation up to 10% in the Higgs top Eucharia and up to 15% in the self-cut of the Higgs are allowed by the experiments in these schemes. We analyzed the signal of two physics in the Bloom-Bloom to HH process. The ingredients, the new ingredients are the modified coupling of the Higgs, the S-channel exchange of the capital H, which is the other CP even Higgs, like in the model. New heavy tops in the loops, but also a new quartic coupling, HHTT, which is typical of pseudo-number Gascon-bosons. These ingredients are very important because both in the resonant and in the non-resonant modes, they adhere to a change in the integrated cross-section and to peculiar kinematic features due mainly to the interference between these we make the numerical analysis of the Higgs production cross-section through nuclear fusion by adapting the public code H-pair by microscope, which is here. That has been extended to include the decoupled HTM. This is the result for the non-resonant full cross-section. We can reach twice the value of the standard model prediction. And this for the resonant. The blue points are the points which are already excluded by the experiment. Okay? The new effects due to the composite scheme are the heavy top partner contribution, which can increase the total cross-section up to 2 times the one of the standard model, and also the new quartic contribution, which can give interference both constructive and destructive, depending on the site. Anyway, the largest cross-section are the resonant ones and are not affected by this new impedance. Another, and this is the last important feature which is typical of these models, is the fact that the new Higgs can have a sizable branching ratio in a pair top and top partner. That makes it possible to have a width of this extra scalar, which can be around 10-20 times the mass. And this is a characteristic which is typical of this scheme, and it is not present in, for example, type 2 HTM or Frigo-aligned HTM. And of course, the fact that we have a broad capital H, this can give an enhancement of the cross-section and has a great impact on the shape modification of the differential distribution due to the interference. Let me show only 2 cases of 2 benchmark points, just to show you the distinctive characteristics in the differential cross-section. Mass. This is a non-resonant case. Here you have a very heavy capital H with a very large width, and it is here. And in the lines between the orange and the red are due to the extra quartic contribution. And the other one, the other part, is due to the large contribution from the top partner in the cross-section. This is for the non-resonant case, and this is another example for the resonant case, a case in which you can clearly see the brightly green corresponding to the H resonance, but also you have a very large contribution both on the quartic coupling and from the top partners. For example, you start to see here the threshold shape, which is used by the boxes in which these top partners are exchange. Of course, these results are primarily of theoretical nature and serve to demonstrate that we have a computable framework within composition areas that can be tested experimentally. This is my conclusions. Okay, I think I win.
Right, hi, I'm Matthew. I'm going to tell you, you want lunch, I want lunch. We're on the same team. So I want to tell you about my work on the Migdal effect with my awesome collaborators. I'm also Irish, of course. I'm from Galway on the West Coast. I went to undergrad down the road at Trinity, and since I left there, which is about 17 years ago, it's the first time I've been back in Ireland for physics. So I want to thank the organisers, particularly Venus, for putting this on, and I'm very excited for Ireland to be joining CERN. So I'm going to be talking mostly about atomic physics, but my motivation is coming from dark matter, which exists. One of the ways we know it exists is from galactic rotation curves. So I've got a couple of historical tidbits, well, two really historical tidbits in my talk. The first is this thing down here. This is the Leviathan of Parsonstown. So between 1840 and 1920, this is the largest telescope in the world. It's about an hour west of here. It was built by the Earl of Ross in the garden of his castle. Private industry, I guess. And what he was interested in was that the hot thing then was Messier had published the Messier catalogue, and people want to know what these mysterious nebulae were. So he built it to look at those. And so in 1845, he was looking at one of the Messier objects and saw that it had spirals in it. And so this is a hand sketch from 1845 by the Earl of Ross of a spiral galaxy, which is this one, actually, the Whirlpool galaxy. And I think this is the first image of a spiral galaxy. He didn't really know it was a galaxy that went around. Anyway, so astrophysics and cosmology tell us that dark matter. But, I'm a particle physicist, and I'd like to understand its particle nature, and that's why we do direct detection experiments, right? Where dark matter comes in, scatters off some experiment here on Earth, and we look for the nuclear or atomic recoil that results, okay? So I want to talk to you today about the Migdal effect, and this is basically defined as atomic ionization or excitation following a nuclear recoil, right? So a neutral particle comes in, specifically neutral, so it's dark matter, or it's a neutron or something like that, scatters off the nucleus. The nucleus recoils off in some direction, the dark matter goes away, we don't care what it does anymore. And so this positively charged recoiling nucleus, the electron cloud sees it flying away, decides it has to catch up, and as the electron cloud catches up and the whole atom recoils, it's possible that you can have an excitation, so an electron going to an excited state, or an ionization where an electron flies out of the atom. This is my second thing I want to say. This is not Migdal. This is it's a random old guy I put in my talk. This is George Johnson Stoney, who was also a 19th century Irish physicist. So he got his doctorate down the road at Trinity and then became professor of physics at University College Galway, near where I'm from. And so he was thinking about atoms. This is just post-Boltzmann. This is 1880s, 1890s. And he sort of hypothesized that as matter is also made of atoms of matter, that electricity might also be made of atoms. And so there could be atoms of electricity. And he thought, well, in that case, there should be something like a fundamental unit of electricity, like an atom is a fundamental unit of matter. And he called in 1891 this fundamental unit of electricity electron. And so that idea is due to him, which influenced Thomson 6 years later, discovered that. So this is something that we're interested in now, particularly since I want to shout out to this foundational paper of Masahiro Ibe and collaborators 67 years ago. The idea of the Migdal effect itself goes back to 1939. And so this Migdal effect is now driving the global, or part of the global low mass direct detection effort. And that's because experiments have thresholds. Right? And so as dark matter gets lighter and lighter, imagine you could tune the mass. At some stage, the nuclear recoil energy is going to be below whatever the threshold of your experiment is, and you're not going to see that anymore. The recoiling nucleus in an atom is not dumping enough energy into your experiment for you to see it, so you lose sensitivity. Now, if you take this Migdal effect into account, even though it's a rare effect, this Migdal electron can be above the threshold. It's much, much lighter. Right? And so if you go and search for these electrons in the data set you already have, that allows you to derive new limits at lower masses from the data you already have. Right? So this is from Sensei. And basically, all of this stuff here below a GeV is coming from searches using the. So we can continue to explore this further in the dark matter sense. The best thing you could do, part of the reason that you're losing sensitivity here is because lots of these experiments are made of heavy stuff like xenon. And if you want to search for low mass dark matter, the recoil on the xenon nucleus is not amazing. And so the best thing you think you could do would be to make an experiment entirely out of hydrogen. Now, I'm not an experimentalist, but I think I'm told that's something slightly fraught. But there's an idea that's out there coming from LZ, which is to basically take the LZ experiment, which is like 8 tons of liquid xenon, and pour a bucket of hydrogen in the top, basically, right? So this is called HydroX. And this would be great because then it's already known that you can, in fact, dissolve hydrogen and xenon at percent levels. There might even be some evidence that this is for helium data, that you could discriminate between like helium recoils, so this is alpha particles, and recoils on xenon and stuff like that. So there's an R&D program going on at the moment to see if this is something that they want to do or is feasible. There's lots of questions around it still, like if you pour a bucket of hydrogen in your experiment, does it ruin the cryogenics? Can you get rid of tritium, etc., etc. And so we thought, well, a cute thing to do would just be to say, if you hydrogen doped LZ, you could also do the Migdal effect on the hydrogen, and that would be like the best sensitivity that you could get to low mass dark matter. And that's what we find, right? So for spin independent scattering, you could extend, depending on exactly what your electron threshold is, rule out all this parameter space down here. But where you'd really make big wins if you did this is in spin-dependent scattering, right? Because if you put in hydrogen, that's just a single proton, and spin-dependent scattering on xenon is not very good. But like having hydrogen would be fantastic because it's light and it's just a single spin on that proton, and you could then rule out all of this parameter space there. So extending from some huge EV right down, all this stuff would go away. So this would be quite exciting. So although we're using the Migdal effect at the moment to set, now and in the future, all of these exciting new limits on low mass dark matter, it's all using these theory calculations, right? These calculations of eBeta, which we've updated. And so you might ask, is there direct evidence for this happening, right? Is there direct evidence for the Migdal effect where I have ionization after neutral particle scattering, which is important because I would like to, not me, but experimentalists like to calibrate their experiments to certain signals? And the answer is no, right? So since 1939, no one has really ever gone and seen this happen, partly because they haven't actually done experiments to look for it. It is known that there's evidence for this from alpha and beta decays from experiments in the 70s, right? So if you have a beta decay, electron flies out of the nucleus recoils, and you can get a Migdal type effect happening that way. But because the dark matter community, direct detection community, has become really interested in this, there's now quite a lot of proposals to do neutron beam experiments to make the first direct observation of the Migdal effect, and then to do calibrations of dark matter. So these ideas look something like this. This is a cartoon of an experiment which is also called Migdal. You take a neutron generator, so some fusion source, and these things are at specific energies basically, so 2.5 MeV for deuterium DD source, or 15 MeV for one of these ones, and they have huge fluxes of neutrons coming out. It's like 1 billion neutrons a second. And you just fire that at something. Something that you're interested in from a dark matter perspective, so xenon in either liquid or gas form. And that will give you a nuclear recoil N and an electron or a bunch of electrons. So there's a whole bunch of experiments and experimental proposals which are out there, right? So these people have done an experiment where they take Lawrence Livermore lab, where they take one of these sources here and they just fire it at a xenon, liquid xenon TPC, the time projection chamber, and has some neutron detectors behind. So you can ask me about the results afterwards. This is a proposal from Japan for something similar. This is a picture of the Migdal experiment. So this thing here that says interaction volume with a bunch of gas. This is their interaction volume, which they'll be having gas in. This is an optical time projection chamber. So you put a camera here on the bottom, camera here on the top, and they can image, optically image, because this is still gas, both the nuclear recoil and the electron recoil, right? So these guys are basically, they have an experiment with FILT at the Rutherford Appleton Laboratory in the UK. You can ask me about it after, but they've basically done a couple of science runs already. They don't have any results out. They're hoping for something for the summer. And the fact that this experiment in particular was happening when we built was the motivation for the calculation I'll tell you about now. So this is all just atomic physics, quantum mechanics. Right, so how do we calculate the Migdal effect, these ionization rates and probabilities? Well, basically, if you're, the electrons in this atom, imagine that you're actually now in the rest frame of the nucleus. The nucleus gets boosted out, so from the nuclear perspective, the electron cloud gets boosted off in the other direction, right? So our ground state, the initial state that we want to calculate this matrix element is psi I, which is the initial state, so that's the ground state of the atom, acted on with a Galilean boost, whose velocity is the nuclear recoil velocity. And then you take the inner product of that as your initial state with the final state, and the final state is just whatever you want it to be. It's the atom with one ionized electron, or 10 ionized electrons, or whatever. You can calculate these things. Now, how do you calculate this? The approximation that's been made until now by eBay and friends is to make a dipole approximation. And that means you take this exponential and you just expand it to linear. Now, psi I and psi f are different. This one will go away, and then you just have this term here, which looks like a dipole. This gives you only single electron operators, so you only see, if you calculate this, single ionizations or single excitations. And you imagine it only really works at small recoil velocities. 10 or 5. You're all getting too much into it. Unless you ask too many questions. Okay, so making a small velocity expansion is kind of okay for dark matter, because we know that dark matter is cold, it doesn't move very quickly. And so this is just like a cartoon of if you had sort of the dark matter and neutron energy, you're both about a GeV, versus the recoil velocity. For dark matter, you know you're going to be down here with the recoil velocities. But these experiments which are currently being proposed, the neutron energy is pretty big, up to like 15 MeV, and so you know that the recoil velocity is actually going to be pretty large. So you're well outside the regime where you might trust this type of expansion. And so what we did was we wanted firstly just to not make this experiment, keep this exponential factor up here, to understand then the possibility of multiple ionization. Right, so this you can only get single ionizations here, but the harder you hit the nucleus, the more electrons you imagine you might take off, and that's true. And make some technical improvements on the treatment of atomic physics of eBay. Okay, so that's what we wanted to do. What we did, and the details don't matter that much. Well, the details matter, but not for this. So then you can make plots like this, right? So this is actual results. So this is for helium, right? Helium is a nice sort of poster child example because it doesn't it's only got 2 electrons. So we can solve the problem entirely, right? So nuclear recoil velocity here, how hard the nucleus is recoiling, and probability of something happening. So obviously, if you don't hit the nucleus at all and there's no recoil velocity, with probability 1, you just have nothing happen. You stay in the ground state, right? So this line here is basically the probability for the atom to stay in the ground state. You hit it, the electron cloud catches up, and that's it. There's also some probability, which is small and becomes larger as the recoil velocity increases, that you have a single ionization. Helium and some single electron flies off. And at low velocities, this looks kind of like V squared, and so the eBay calculation, this corresponds to this little bit down here. But as you hit the nucleus harder, you might imagine that you get a double ionization. Effectively, you hit the nucleus and it flies out of the helium atom, and electrons are just left sitting around wondering what's happening. And so as you increase the velocity, indeed, the double ionization rate increases, right? And then that's all that can happen, right? There's only 2 electrons in the problem, and so if you add together the probability of nothing happening, so the ground state plus a single ionization or a double ionization, you get the blue line, which is 1. Like a unitary. And that's all that can happen here, right? So you do see that as you increase this nuclear recoil velocity, that you get more multiple ionizations. Wait, who said that? Oh yeah, so there's a difference here between, okay, good. So we can distinguish in our calculation between ionization and excitation, right? So where you go from the ground state to an excited state of the atom, or to an ionized state. And most of what you get is it's more important, you get more ionization than excitation, basically. Okay, so because happily one of our collaborators in this was a relativistic atomic theorist, but we thought it was a good idea to check things, so we did it twice. So this plot now is showing, so the difference between the solid and dashed lines is now between 2 different atomic physics codes, 2 different calculations we did. One is with a code called Bertha, one is with a code called Grassmann-Ratib. So these are 2 independent codes which use 2 independent methods of solving the relativistic Dirac-Hartree-Fock equations. Okay. And, the Herwig and Pythia of atomic physics. And you can see here that, so we can go up to triples for neon, there's more electrons in the game. The bottom plot here is showing the ratio, the difference, the percent level difference between our 2 calculations, which is at a couple of percent, basically, right? So we feel like we have control over what we're doing at this sort of the percent. Now, for computational reasons, in neon and in any problem, we can go up to sort of triple transitions. So we can calculate exactly for you, or relatively exactly, what's the probability of 3 electrons or whatever. But it becomes harder above that just because it's just combinatorics, essentially. And so at larger velocities, we just can't calculate 4. And so if you look at essentially this sort of like parity line, when you add together all these probabilities, probability is essentially conserved up to sort of here, but then because you're not taking quads and above into account. Okay, so if you're ignoring these sort of multiple ionizations and above, is this a big problem for any predictions that you want to do? Because this is, some of the experiments will be operating this year as well. Okay, I'm going to argue to you not really, and that's again because thresholds matter. Okay, so it's not really the probability. You don't really care about the probability of ionizing 1 or 4 or 9 electrons. What you care about is how many electrons do you have above your experimental threshold. Right? And at large recoil velocities, nuclear recoil velocities, we find that the observable rate is dominated by many orders of magnitude by having 1 hard and multiple soft electrons. So here I'm showing you the similar kind of plot, but now we put a threshold on. So you only appear here if the electron energy is above 1 keV, which is indicative of all the experiments that are going to happen. So if you have, a single electron, a single ionization, that's this dashed line, so you get a single electron here and then it falls away if the electron is above threshold. Now the 2 purple lines are the kind of the interesting ones. We can calculate the probability of having a double ionization where both electrons are above the threshold, which is the solid one, and the probability of having 1 hard electron and 1 soft electron. And you can see that by many orders of magnitude, you're just going to get 1 hard electron and multiple soft. So even though you have to sort of take multiple ionizations into account to get the right answer, you're actually ever going to see the 1 electron.
What's carbon there mean? What's carbon there mean?
Carbon, it's a kind of element.
Carbon on it.
You use it to calculate the recoil. So if you choose
No, this is for the carbon atom. Right? They all have, you can do it for different atoms because they all have different electronic configurations. And this example is done, this is for a carbon. So the relevant calculation you really want to do is what we call a semi-inclusive probability. So this is you have to calculate the probability for a single ionization above threshold and all the others being soft, basically. So you can write this down like this. So the probability of going from the ground state to a single hard electron chi with all the other ones just being soft, which you can write as you calculate this matrix element and you sum over the n-1 other electrons below threshold. And so we argue in the paper that you can basically approximate this thing, which is tricky to calculate, in a relatively compact form down here, which only involves single electron operators. This is an approximation. It breaks down when you hit things hard enough. But for any experiment that's going to happen, you're never going to hit things this hard. And that's this semi-inclusive line up here. So even though we can only precisely calculate for up to triple transitions, using the approximation, we can calculate this line, which should incorporate the effects of all of the multiple transitions, right? Because they're all soft. It's like a resumming. So that means that we can make predictions and feed this into the experimental collaboration, right? So we've calculated this part out here, and then you just have to fold in neutron nucleus cross section, all this other stuff, to get an actual rate. Okay. One other trick, which I can talk about if you want to ask, is that we treat a molecule as a bunch of atoms. So these are predictions that we, for fluorine. So the actual Migdal experiment operates with CF4, which is another which is a horrible thing. But basically, you can see there's we should certainly know you have to incorporate the effect of multiple ionizations, right? So this line here is if you have single ionizations, if you have doubles, and so certainly out in these large recoil energies, if you're not taking into account all the multiple ionizations that can occur, you're going to get very different answers. Okay, so as promised, I've come in under time. So we've revisited and improved calculations of the Migdal effect in a variety of technical ways, but also necessary ways for understanding current and future neutron beam experiments, and which are also relevant. Right? We have done a better job than Ipe et al., even on the low velocity calculations relevant for dark matter direct detection experiments. Okay, so we did this so you don't have to. Okay, so. If you ever want to, all these results all are all publicly available online for a large number of different kinds of atoms, CF4 and all the noble gases and that kind of thing. Okay, so thanks very much.